to write a Verilog. So to continue from yesterday's class, just to give you some overview about what we did yesterday, we were exploring the Verilog codes for some counter, and then we were also looking into the FSM Murray and Mealy state machines. Now today what we will do is we will try to go into certain aspects of the of further certain aspects further. So now you have written your RTL, you have written your Verilog. What is next after writing your Verilog? What is next? Can anyone tell me? Once your RTL is ready, what is the next step that we have to go for?
Stimulation.
Yes, Ramya, can you be a little louder?
Stimulation.
Simulation also we have seen yesterday, right? Writing test bench and simulating it, and we have seen the waveform also.
Fabrication.
Come on.
Fabrication.
Yeah, fabrication is the final step. But what is the next step after writing?
Synthesis.
Verification.
Somebody was saying synthesis. Who was it?
Me, Rohan.
Yeah, Rohan. So it is next step is going to be synthesis. Okay, what a synthesis means is right now, whatever you have written the RTL, it is going to be on your laptop and it is going to be getting written. I mean, a test bench is written over it, and then you simulate it. You see whether your RTL is going to is working fine. It's meeting your functionality requirement. So whatever you have seen, it is all like very small designs. Okay, it is like some 10 lines of codes or 20 lines of codes. With this basic understanding, you please go into your RTL coding part and learn more about like how do you implement a small ALU, arithmetical logical unit, which is quite a big chunk of code that will be there in that, which will have good amount of logic and sequential parts. So when you are writing some such kind of big designs, also a processor, at least a pipeline, two-stage pipeline processor, if you're going to construct, which is a minimal size of a processor. If you are designing such kind of designs, the basic first step that you will do is you will simulate it. You will verify it functionally whether it is working correct or not. As a designer, you will do that. The second and the next step that it will go to is it will go to the step of called synthesis. Okay, let me use my pen and iPad. 1 minute. Is are able to see?
Yes, sir.
Yeah. So once you have done your RTL and then you have done your functional verification. Functional verification is nothing but writing a test bench and simulating the design. Next step will be synthesis. Okay. So in synthesis, what will happen is whatever you have, 1 minute. Satya sir, have you joined? Okay, I think he is going to join late because if he joins, then he will ask me to repeat it once again. So that's why I just confirm. So once you have started with synthesis, what happens in during synthesis is whatever you have written in your RTL code, say you have written a design for a counter, like yesterday we have seen, right? And it will have, if it is a 4-bit counter, it is going to have 4 flip-flops inside that. Now, whatever you have written in your RTL are going to be just a, what do you say? It is going to be just, it is not getting translated to any equivalent hardware. Rather, it is just being as a software only, soft written code only. It is going to be on your laptop. That means during synthesis, what happens is it has to map, your RTL has to map to a technology hardware. What does this means is, suppose you are going to fabricate fabricate this design on a 22 nanometer, suppose you're going to fabricate it on a 22 nanometer uh, TSMC. TSMC is a foundry. You're going to do a tape out using this. Then whatever you have designed in the RTL, the Verilog code, has to get translated to the components of this technology. Like you will have in this, you will have your AND gate, OR gate, flip-flops will be there for this particular technology. And this the written RTL Verilog code has to get translated to the components of this technology. So basically, the mapping of your RTL to the technology hardware is called the synthesis. So a synthesis is basically you will have two types of it. One, it goes to FPGA based, and then it goes to ASIC based. FPGA is field programmable gate array. ASIC is application specific integrated circuits. Okay, so what is the difference between them? So FPGA is a field programmable gate array, means it is like a platform. Basically, it is a hardware platform. It is a chip. FPGA is a chip by itself. So you will have a board, FPGA board. There are a lot of vendors like you have Xilinx, RT, Xilinx, and then you have Quarters. These are the major vendors. These are the FPGA providers. In this board, you will have an FPGA chip. If it is Xilinx, there are a lot of chip families you have. You have Spartan, you have RT, RTX. Yeah, there are a lot of family in this. So these are the FPGA chip names. These are the FPGA chip names. So what happens is once your RTL is 1 minute. Once your RTL is ready, once you have completed your Verilog and you're coming to the process of synthesis, and FPGA based synthesis, what will happen is your RTL. Just a minute, it's not, I'm not able to write it.
Sir, I have a doubt, sir.
Yeah.
What about CPLD, sir?
CPLDs are also another set of families for that falls into this FPG only. They are like it's an evolution that has happened. There is like this CPLD families of chips are available like you have for FPGA. In a CPLD, there will be some components which are programmable and some components will be like it is already done. There will be a available logic inside that which can be used like that.
Got it, sir.
Yeah,
Yes, sir.
that's all.
I have a little bit more doubt, sir. Like,
Yeah.
how do this exactly work, sir? Like, FPGA has a lookup table based structure, but how
Yeah.
does the CPLD look like at the transistor level?
Both are implemented at the transistor level only. See, there's what CPLD you are saying is complex programmable logic. Is a certain pattern of basically in FPGA you will have lookup tables and then you have CLBs, combinational logic blocks are there. It is two different what do you say patterns of chip that is getting manufactured. That's all.
Yes, sir. Got it, sir. Thank you, sir.
Sir, what about SoC, system on chip? It will be fall under FPGA or SE?
No, SoC is not at all related to this. And who was that? The CPLD who was who was it?
Yes, sir. Jayavardhan.
Jayavardhan, CPLD, basically, you will have this PLAs and all inside, right? That there will be programmable logic array and all will be there. In FPGA, also you will have this programmable logic array in a different way. So I'm saying CPLD and FPGA are like more or less are same. They got evolved. CPLD then got evolved, and now people are using mostly FPGA only.
Yes, sir. Like, I want to know about the topology of it, sir. Like the layout.
How it's there inside, is it?
Yes, sir. Like the differences between in the structural level.
See, structural level, if you see, there will be logical cells in both the things. Okay, logical cells. If you see, how do I tell you? Yeah, in CPLD you will have smaller number of logical cells. In FPGA you will have larger number of logical cells. And the interconnect structure also inside the FPGA, it will be like it will be more flexible inside a FPGA. But inside the CPLD, it will be more like a very fixed a rigid interconnect where the interconnects are not configurable. Only the logic is configurable. You do understand what is an interconnect is?
Yes, sir. Is it like connecting multiple subunits like CLB together?
No, no, no. Interconnect is like, see, if you are writing your RTL, Verilog code, and it is getting translated, it is when you are dumping it in an FPGA or CPLD chip, okay. Between one gate to another gate, there will be a connection, right? That has to happen through net.
Yes, sir.
That interconnection is not flexible in CPLD, rather it is flexible in FPGA. It is okay. So Jayavardhan, what I will do is like I'll try to get some data on that, and then let's have it separately, because that is going to be a separate topic.
Yes, sir.
Fine.
It's fine, sir.
Okay, 1 minute. I was just fixing my tab. Okay, you're able to see now? Okay.
Yes,
So
sir.
we were into synthesis. In synthesis, it is of two types, FPGA based, and then you have ASIC based. In FPGA, I was telling that it is going to be a board. In that there will be a chip, FPGA chip. So what you will do is you will, whatever RTL that you have written, you will dump it here. You will dump as in you will, one minute. Yeah, you will dump your RTL inside this FPGA chip. So in this FPGA chip, we'll have some of the predefined cells inside the cells, as in you will have some logic cells, combinational logic cells, and you will have some sequential logic cells. What is happening in this? Okay. So inside this FPGA chip, you will have logical cell, combinational logic cells and sequential logic cells. What does that mean is, if your Verilog code, in your Verilog code, you will have, suppose you have designed a counter, counter.v. In this counter, if it is a 4-bit counter, this 4-bit counter, what is it happening? Okay, no, it's not. So you have this 4-bit counter. In this 4-bit counter, you will have 4 D flip-flops. Now this 4 D flip-flops plus some combinational element. Like you'll have some AND gate or gates. So what it will happen is once you have written your Verilog code, it will get dumped into the FPGA chip. Inside this FPGA chip, you will have certain logical cells that will get mapped with your counter Verilog code. Some sequential cells that will get mapped to your Verilog code. So what is the entire process from synthesis? Synthesis on FPGA that is happening is your RTL is getting translated to, it is getting mapped to hardware. So on this context, what I'm saying is, you will have to write a Verilog code that has to be synthesizable. You cannot take up any code that can have elements. There are some elements in Verilog which are constructs, like they are non-synthesizable constructs are there. Anybody is aware about this non-synthesizable constructs in Verilog? Okay, we'll go into that. We'll see that. So this is one type. This FPGA based synthesis is another type. So you have ASIC based, right? So we will be going with this flow. This ASIC based synthesis only we will be going. This FPGA based, we will see. We have seen a little bit on this. We will mostly not go into this FPGA based synthesis and prototyping. We will go into. I have given you a brief understanding on this. In ASIC based thing, what will happen is here only the technology comes into picture. Say you are going to fabricate in a 22 nanometer technology fab, TSMC. What will happen is your RTL, whatever you have written, your RTL will get mapped to the components of this library, components of this I have said that it's library. Library is nothing but all the cells, all the combinational / sequential elements are called as library cells. So this, how does this happen? How does this happen? This happens using the EDA tools. This process happens using EDA tools. You have Cadence and Synopsys are the major tool who does this. Process of synthesis. I mean, they do a lot of things. The first step that is in this ASIC based flow is you have to convert your RTL to a netlist. I'll come to that. What is a netlist and all is. Basically, you are going to do your RTL to get mapped to a technological cells. This mapping is carried out using the EDA tools. In Cadence, the synthesis is done using Genus. Genus is a tool, one among the tool in Cadence, which is doing the synthesis. In Synopsys, it is design compiler. Design compiler. One minute.
Sir, I have a question.
Yeah.
Hello. Sir, which one is used more now in industry, sir?
Both of them are used. It is not like it is. It is not like. It is not like only one is going to being practiced industry. Both of them are used.
Okay, sir.
Someone has a question in the chat. At which phase is VC spyglass is used? Smita, spyglass is will be used at various places. One major usage of spyglass is for whenever you whatever your RTL you have written, whether that RTL could be is it a synthesizable RTL or non-synthesizable RTL, that itself you can see using spyglass. One thing. Second thing, you have in RTL if you are using multiple clocks in your design. Say you have three clocks in your design, and there should be synchronization has to happen between whenever you are using these three clocks in your design. So if there is any clock domain crossing happening in your design, that may lead to misfunctionality, as well as your chip might not function also. To check that whether your design will function in those particular corners, those particular corner situations also, you need the spyglass tool to validate it. I think I have answered. You have any other questions?
Thank you.
Okay. Okay, now we will see what all things in Verilog are non-synthesizable. What all if while writing here. So this is the RTL guidelines that you will have to ensure. So non-synthesizable constructs. So non-synthesizable constructs means basically those will for example yesterday we were writing a test bench, right? In test bench if you see there are there are like some delay elements you have added, right? You remember, guys, remember delay elements? Like you gave hash
Yes, hash.
10, yeah, hash 200. These are there is no hardware equivalent, there is no hardware equivalent to this. Okay, so that is why these delay elements, if these are there in your main module. See, in test bench, you are only writing to verify your functionality of the Verilog that you have written. You are not going to take that forward for manufacturing of the chip. You will be only taking your main module. In your main module, you should not have these kind of delay elements while writing the Verilog code. Then you should not have initial statements which you had in your test bench. You remember? You guys remember that initial statement that you have?
Yes, sir.
Yes, sir.
Yeah. So then in the test bench itself, you have seen dollar finish. That is also non-synthesizable. And then you have dollar dumpware was there, no? That is non-synthesizable. Then you have yeah, main thing is this file input output operations are there, where you will read some file through your Verilog. You read some hexadecimal file, some boot code file and all, like. So those are done using this keyword called read memh. read memh. This is a Verilog keyword where you will read the file. For example, you are going to read a hexadecimal file, file.hex, which is a memory. So if you are going to read this file.hex, which is outside your written Verilog code, you are going to read a separate file. This read memh will import that file to your design. So these kind of file operating, like reading and writing to a file, reading a file is not synthesizable.
Time scale also, will it be
Yeah.
counted?
Timescale, yeah, that is also not synthesizable. That is not going to, that is just for simulation purpose we have added, like your dollar finish is there, no? Like that.
Okay.
Yeah, some more majorly I have covered all the non-synthesizable thing.
Good morning, sir.
Yeah.
So could you just tell me what this dollar finish and dollar dumping is?
You were there on yesterday's class?
No, sir, I couldn't attend yesterday's class.
Okay. Yesterday I was showing a test bench. Okay. In the test bench, I have written this dumpware and dollar finish. Maybe I'll see if I can show you that. 1 minute. You guys are able to see my screen?
Yes, sir.
Yes, sir.
So if you see this, this is what I was showing yesterday. You have, this is the Verilog mod. This is the main module for a counter design, where this is a 4-bit counter, which starts counting from 0, 1, 2, 3. This counter has input as clock, reset, and output as count. So in the test bench, if you see, I have declared the registers for all the inputs and declared a wire for the output, and instantiated the counter in the main module counter inside this test bench. I have instantiated it and given the instance name as DUT. Here I'm generating the clock. I'm starting to generate the clock here. It goes on. So here, if you see, I have the initial statement, which is a non-synthesizable thing. And here you have the dump file and dump wares. Here, what you will do is dump file is will dump the VCD for. So I have given a .vcd where your simulation will be dumped inside that file, and that file can be opened using a waveform viewer, and you can view the waveform. And dollar finish is like after 200 cycles, 200 picosecond, your entire simulation will get over. If you're not giving this dollar finish, then the simulation will go on and on. It will not come to an end at all. So that is the purpose. And once your VCD is dumped, so I have dumped the VCD here. You can open in any of the waveform viewer, like I have GTK wave. So here you are pulling all the signals. So this is the waveform which for counter it starts like counter starts from 1, 2, 3, 4, 5, 6, 7, 8. So this if VCD is not there, if you're not dumping the VCD, then you will not be able to see this waveform. I hope that clears.
Sir, one request, sir. Can we go through that FPGA flow once, sir, in the synthesis actually? There is a netlist that you explained once.
That was initial part, sir. So you joined late as well.
Yes. I joined late, sir.
Okay.
Or otherwise, I can go through the recording, sir.
Yeah, I think that should be fine, sir. I mean,
Yeah,
it
yeah.
is very clear. If you
Okay.
just look into the recording
If it's
itself,
straightforward, yeah. Fine.
it is straightforward, sir.
Okay.
If there is any doubt, sir, you can
Definitely.
ask me in the next class. I will be able to help you.
Definitely. I'll note down, sir. Thank you.
Yeah. You guys are able to see my screen? I'm shared it.
No, sir.
No, sir. Share screen. Okay. Yeah, now right? Now you're able to see. Okay. So so these are some of the non-synthesizable Verilog constructs. These should not be used inside your main module. In Verilog, you will write you have main module and you have test bench. A test bench will not be taken further. Test bench is only used meant for simulation. Only main module will be taken further for the synthesis process. So this only will go through all the process and finally it will become as the chip. Okay, so this is what I want to say, and yeah, these are some of the RTL guidelines that you have to ensure. Other than that, I have one more slide that I wanted to share with you. 1 minute. Uh, just give me a moment. You're able to see the screen?
Yes, sir.
Yes, sir.
Yeah. Okay. So let's have a brief overview, like what here. So your RTL is ready, and now what is next? We are going to synthesis. What all? The steps that is there in this industry? Somebody was asking me what are the domains in this industry? Like what are the job opportunities available? What kind of job opportunities are available? So I think this slide will give you that level of understanding. So are you guys eager to know?
Yes, sir.
Yeah. Who was that who was asking this? Like somebody was asking, no? Is he in the class?
Sir, Marufa.
Yeah, Marufa. Okay. Yeah. Oh. So right now we have crossed 2 stages. What can somebody tell me what all stages we have crossed among this in this all the blocks? What all we have seen?
RTL and synthesis.
Synthesis we haven't crossed. We
Okay.
have just entered.
Test
RTL
bench.
design.
Huh?
RTL design, RTL
Uh,
design,
Yes, and there is one more also.
simulation,
test plan, test
simulation.
plan D.
Yes, Anirudh, you wanted to say something?
Product specification.
Yes, good. Yeah, you have crossed product specification and RTL. What is product specification? You wanted to design a counter, so you should say about my counter should count from 0 to 15. It is a 4-bit counter. These things are like you have to write. There should be a documentation necessary for designing the counter, right? So that is the product specification. For designing a hardware, the first step is we should know what is that our hardware is going to do. How do you do that hardware? That will come to in your Verilog. While writing a Verilog, you will know, like you will decide how do I implement this, whether I'm going to implement using a structural way, or it is going to be a data flow way, or it is going to be a behavioral way. I'm going to implement, or if I'm going to do a mixed, I can use it like structural plus uh, behavioral, or data flow plus behavioral. These kind of decisions only can be taken once you know what to do. What to do can be you'll be getting it from the product specification only. Product specification, you as of now, whatever I have taught you, right? You may think that it is going to be very simple. No, it's not going to be like that. Product specification, you will have lot of modules inside that. It like there will be lot of teams working inside one each task. For example, if you are going to design uh, processor, you will have its own control units. It's have its own arithmetical logic unit. It will have its own fetch unit, decode unit. So uh, for a simple processor itself, I'm saying processor itself is a simple design. Then think about whatever we have done now for counter and D flip flop, all those things. Those are nothing. Those are like very, 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 very basics. Okay. Now, if you are going to design a processor, a simple processor, you will have these kind of blocks. You have um, uh, you have control units, you have arithmetical logic units, you have fetch, decode, execute, memory units. You have the interconnect bus that is going to connect between uh, the peripherals and the core. Somebody was asking about an SOC. See, SOC is a SOC is an RTL. Okay, SOC is a Verilog code that you write and bring that design as an SOC. SOC is what? You have a processor, you have the peripherals like UART, like GPIO, these kind of peripherals. You integrate everything together, so it forms as a system on chip. So by a chip by itself is functioning as a system. Uh, so that becomes a SOC becomes a RTL. It does it is a Verilog code by itself. Okay, you write a Verilog code for your SOC, and then you take it to FPGA based synthesis, or you go to an ASIC based synthesis to implement your SOC. Uh, I think the doubt is clear. It was by Biswajit or somebody else.
Yes, sir. Yes, sir. Yeah, yeah. Got it, sir.
Yeah,
Thank you.
yeah. So now here in the product specification itself, there will be multiple teams. Each team, for example, each RTL team will have a minimum of 5 to 6 people for working on a simple ALU itself. For ALU, you will need some 2 to 3 person who is going to design it, and then you will have to verify it. Okay, so that is the explanation for this product specification block. Okay. Any doubts in this block?
Sir, just one more question. When you're saying product specification, is it the architectural specification also and IP specification also? Like if it is like considered, there will be different teams, right? Architectural specifications will be taken by the SOC architect, and IP specification will be dealt by by the IP team. So how is it like, how would they be referring to it, like product specification? They will be working, they will be referring the product specification or architectural specification. As per my understanding, it
Oh,
is
yeah, yeah.
architectural.
Yeah, no, no. So the thing is, product specification will have details about everything. We'll have details about your architectural specification. We'll have details of your IP specification. For the understanding of this, other people in the class, let me tell you what is the difference between a architectural specification and an IP specification. Architectural specification for a processor is being taken from the ISA that is provided by say RISC-V ISA, or from Intel, or from anyone. So the ISA will tell holds as a specification for designing a processor. So uh, for processor will be considered as an IP in product specification. Processor will be considered as an IP, and there will be other components of for that processor, like the you have your uh, peripherals like UART, like you have GPIO, PWM, SPI. These are some small peripherals, and you have USB, you have HDMI. These are some bigger peripherals. So each peripheral is also considered as each IPs. So there will be separate specification for each of this peripheral. Uh, all these will become as a one chip. It is going to be become as a one SoC chip. So this is going to be the specification for the chip. Okay. Now this chip is going to, once it is in manufacture, it is going to sit on a board, and that board is going to become as a product, like board as in your mobile phone. That mobile phone is going to become as a product. Now there will be a other specification other than the chip, like what all other components other than the chip comes on the board, whether it will have any other external chip that is going to control the display, any other external chip that is going to take care of the charging of the phone. So completely as a complete product spec will have end to end, like from your chip to the other components of the board, everything will be covered in the product spec. Is that clear?
Okay, sir. Thank you.
Yeah. So you will have see once. So I am just trying to tell you for the betterment of the crowd here. Uh, I'm giving you the insight of wherever you will have job opportunities. First thing is whatever right now I have said here itself, you will have some 10 to 20 openings uh, for each portion of the spec. Suppose you are going to implement, say you are going to implement a USB IP, which is going to be one component of this spec. For implementing the USB IP, you have two components in that USB IP. One, you have the digital components, which you will be writing the Verilog code for that USB, and you have the analog component. Analog component will be handled by you will have to design. You will have to draw layout and design the analog component of the IP. So nearly for writing a writing the implementing the USB spec, you will need some 4 to 5 persons in your team for USB spec alone. And if your design is say like you have a octa-core processor with lot of other peripherals, everything, then the team size will go up from 100 to 200 people. I'm saying for implementing all all IPs and spec related to the SoC. So once your product spec is understood, then you come for this RTL. RTL phase is where you um, write your Verilog code, write your VHDL code, write your blue spec code, where you implement your specification uh, uh, and you check the functionality whether you have implemented it as per the requirement, as per the spec requirement, whether you have implemented the design. So once you have written your RTL, that for example, in our case, we were writing the counter Verilog and the that 4-bit counter that we have implemented yesterday. Once you have written the RTL, which will take around 3 to 4 months of time for generally a big project like processor, if you are writing. Then once your code is written and it started working functionally, if it you see that the code is working as per the requirement, then you take that RTL code to synthesis. Okay. If you're taking to synthesis, then in synthesis itself, you will have the fabrication entity will come into picture. So if you are going to synthesis, then before that you will have to decide to which fab I am going to fabricate it, to which technological fab I'm going to take my design through. So those things has to be taken care. Mm, so what do I mean by that is you will have to pay an advance amount for the fab. Okay. Uh, Once you are paying an advance amount to the fab, that means you are going to target on a timeline and you are going to tape out the chip. Okay. So until this, any doubts?
Sir, how does that blue spec code look like? Um, um, Verilog and um, Verilog and VHDL we have seen, but blue spec I have not seen.
Okay, maybe I'll show you in the next class. I'll take up a design and show you. And it is also available. It's also available. The Shakti processor is an open source processor which is written on the blue spec. So you can see, you can Google it and see the repo and open and see also. But even then, I'll show you in the next class.
Okay, sir. Thank you.
Any doubts? Okay, give me a 2 minutes break. I'll just get some water and have it. Meanwhile, if you have doubts, put it on the chat window. I'll see to that. Or if you don't understood also, please tell me. Okay, yeah. So coming back here, while I was telling about, sir, we are going through. Okay, Ramya, we are not going to go in detail because most of them will be covered in as per the as part of this course. Most of them will be covered. Like you will get hands-on in quite a number of blocks. Okay, so I'll be just giving you a little bit overview of whatever possible. Now I'll give you an overview. What is happening inside each blocks, like what kind of work is being done. That is all is the intention. Is that okay? Okay. Okay. So once you are written your RTL, right? What the functionality you are doing using functional verification. Okay. But actually, if you see, will your when you are verifying your code, your written code functionally, if it is working, say your code has some 4 inputs and 1 output. 4 input you will be passing, say from 0000 to 1111. You will be passing the values and you will be checking the output whether it is coming as per the required expected output is there or not. That you will be able to see it. But for example, if you're for a simple 4-bit itself, you have some 2 to the power 4 test has to be done to validate the functionality of the design. If your inputs are not like 4 bits, uh, it is going to be some, say, 20 bits, say some 200 bits are there, 200 inputs are there, or say some 25 inputs are there. So that is going to get translated to your combination of inputs is going to be 2 to the power 25, 2 to the power 200. So will you be able to verify it functionally? Whether will you be able to see for this particular input, my design is giving this particular output? Will you be able to do that in your functional verification? I mean, are you guys getting my question?
It will be too complex, sir.
My question is complex, or it is going to this
No,
is
no,
going
no. Verification will be complex. It will
yeah.
be huge number of today. 2 to the 25 means how many places will be do the verification?
Yeah. So that's why what the industry do is, when you are writing your RTL as a designer is one job role. Okay. As a designer, you will do your functional verification by writing a test bench a little and see whether grossly you are meeting the functionality or not. You will do a functional verification and see. Then the RTL is given to the designer hand over the RTL to a verification engineer who take this design, and there is some methodologies involved in this verification which will be also part of this course at later part of this course, which Uma ma'am will be covering. Okay, those verification will be that verification that is being taken care by the verification is called as a formal verification. Whatever the designer do, it's called a functional verification. Whatever a verification engineer do, take the design and verify it, that's called a formal verification, where he formally approves that this design doesn't have any issues, it doesn't have any functional bugs. This could be taken forward for production. It can be taken forward for doing synthesis and then henceforth to the fabrication unit. Any doubts here?
So what are the different techniques used in this used by the verification engineer to for the complex design?
There are techniques as well as there are different methodologies involved in this, which will be taken care in this course. Once we'll be coming to that topic, we will see to that. There are UVM methodologies, OVM methodologies are there. So we will come to that. Once this topic comes, we'll come to that. Other than that, conceptually, does this make sense? Are you guys able to get what I'm saying?
So physical
Yes, sir.
verification happens post that, sir.
Physical verification is something that is related to the fabrication process.
Fabrication process. Yeah, yeah.
Yeah, please. Anyone else?
Sir, so is it done through EDA tools only?
Yes, it is done through EDA tools. Once from RTL itself, you will need a EDA tool. From RTL, once you are writing the Verilog from there itself, you will need EDA tools. There are separate tools available. As I said, for synthesis itself, in Cadence, you have Genus, and in Synopsys, you have Design Compiler, right? Similarly, you have verification tools in Cadence as well as in Synopsys.
Okay.
So these are all these verifications fall as part of the synthesis block, sir.
No. It is not there in this block. It is none. It is not in this. Inside, it actually falls inside RTL only. There is no
Oh, it's
verification.
as part of RTL only.
Yeah,
Okay.
yeah. I mean, but actually, you can mention it as a separate block itself. But let's consider that's there inside RTL.
Okay. Maybe after RTL, maybe the verification, then synthesis. Maybe.
Yes. Actually, see, once your RTL is a bit ready and you are able to see that it is able to meet the functional requirement, the designer handovers the design to the synthesis team. As well as he handovers it to the verification team. Verification team will start looking into the design, and then he start to work on that. And then if there is any issue, then he will report back to the designer, whoever is the written as the RTL. He will report that for this particular test, your design is failing. Karke, he will report it. Then the
Okay.
designer will look into the design and see what is causing this, and then he will approve and say that yeah, this is actually an issue. Let me fix it and give you another release. Karke, he will take it and then he will fix it and give another release to the verification team. But it doesn't mean that the synthesis team that has taken it will not will stop working. He will continue to work. Uh, Once there is this engagement between the designer and the verification engineer goes on, like it goes on and on. Like once he fixes and gives, he again then the verification engineer runs the verification suit and see. Once this gets qualified, then the RTL, whatever he has written, designer has written, come to a stage called RTL freeze.
Okay.
So once this RTL is freeze, then again the designer will hand over the frozen RTL to the synthesis team, saying that this design has gone through this many phases, and there is a little bit changes inside the design. Now you can henceforth take in, and this one you will take it for the further process in the tape out.
But is that not a rework for the synthesis team, because they have already started before these changes and there were multiple
It is not
iterations?
going to be a rework. It is going to be an add-on to them, because in the meantime, when this verification team is working, the synthesis team will get familiarized with the design. They are not aware of whatever the RTL has is written inside that. They will not be so they should get familiarized.
Okay. Okay.
So
Maybe they were also given the signal or flag that it is still undergoing verification, so that
yeah, they are
meanwhile they can
aware.
familiar.
They are aware. The entire team will be aware
Okay.
of that.
Okay.
But once,
Okay.
but the first cut that goes to the synthesis
Mm-hmm.
will have some should have some basically protocol. Okay, there should not be any change in certain aspects of the design. Mm, I mean, the first cut, but whatever is given handed over to the synthesis team should
Mm.
not should have some uh, thumb rules, which I'll say it in the upcoming classes. Okay, those
Mm-hmm.
things should not be changed in any further releases from the RTL.
Okay.
Only certain aspects can be upgraded by the designer and hand over it to the synthesis guy. Other aspects
Mm.
has to be maintained, which cannot be changed. Which then it will become a rework for the team.
Okay. So there is a freeze on some of the critical aspects, maybe. Freeze.
There is, yeah, there is a freeze on. Yeah.
There is a freeze. There is a freeze where some of the aspects may not be touched actually.
Yes, yes. I see, sir. Do we need to learn system Verilog for verification, or do we do in Verilog? So you will have to learn system Verilog. System Verilog, now, yeah, it is not mandatory, but you should know system Verilog. You should know. Once this verification module come during, I mean, this session, when verification module comes, we'll address to those things. This is for Prudvik. And then Marufa, as a fresher, which side is easy? No, you should choose. I mean, we cannot say it to you. It is something intuitively you will feel that this is, yeah, this is aligns to my interest. I think this is my cup of tea. You should choose.
Sir, I have a question to ask.
Okay, sir.
Yeah, yeah.
Sir,
Uh,
recently IIT Madras launched a supercomputer called Param Shakti. My question is, India's want to seize play a crucial role by 2030 in a supercomputer field. As a future VLSA engineer, do we have a role in supercomputers, or the VLSA domain and the quantum computing domain is different from each other, or should we gonna play a major role in supercomputers, sir?
So these are opportunities. Whatever you're talking are opportunities. That is now, since the industry is right now booming. Okay, past 50 years we were not concentrating on this industry. Now this industry is booming, and even the government and everything is trying to push this industry so that multiple products, multiple technologies come into. You will have opportunities in all places. Like suppose you are going to want to participate in the national semiconductor mission that the government is running, and in that there is supercomputing design facilities that has to be done. I mean, you can as well be part of it if you're I mean, if you are skillfully qualified, you can also be part of it.
Thank you, sir.
Sir, is MTech a mandatory to be in semiconductor industry, or having the necessary skill is enough? See, if I would say, I'm saying for everyone, whoever I'm teaching until now, I would say if you are able to, if you're affordable for doing an MTech, I would say please go ahead and do, in especially in this industry, because I am a master's in VLSI. So that's why I'm saying if I were a BTech, I wouldn't be, I mean, I'm not sure, but nowadays BTech courses are becoming more stronger. I mean, the content that is there in the BTech course are more relevant nowadays. But still, if you are affordable, I would say please go through, go do an MTech. I mean, MTech in a good university. Uh, I would say please go ahead. This is for Alamin.
Excuse me, sir.
Yeah.
Dhanush here.
Yeah, Dhanush.
Doing MTech immediately after BTech will be helpful, or maybe working for a couple of years or 3 years, like get an experience and then do MTech. Will that
No,
be
no.
effective?
So I would say go do your MTech after finishing your BTech immediately. Because I did my MTech after 2 years of working. After I finished my BTech, then I worked for 2 years, then I went for MTech. I don't see a big difference in that. Actually, I have wasted my
Okay.
time only, I would say.
Okay, because some of the industry experts I have talked to them, they were like, get an experience of a couple years, then apply for MTech in good university, then you'll have much better understanding later.
No, when you are working in the industry, first you should get this job, right? First you have to get a job in VLSI.
Yes.
And if you are doing that way, then okay, then you do the MTech after, if you're getting into this domain, and then you are going to do the MTech, then it is fine.
Yes, yes.
But 1 minute. But if you're not getting into the industry, if you are in some other industry, and then you are wanted to do the MTech after that, then it is not advisable. I was actually working as a as a software engineer for 2 years. Then I did my master's.
Okay.
Yeah. 1 minute. I'll just connect the charger to the laptop and I'll share my screen.
Okay.
Okay. Meanwhile, any other doubts? My laptop got turned off. I'm just logging in again and sharing the screen.
Sir, I have another doubt, sir.
Yeah, tell me.
Sir, if a company seeks to hire a fresher, they will definitely see what type of real projects he done in his as a fresher. So, which type of projects do you prefer to do as a fresher, sir?
As
Real time projects.
as a fresher, if you are if you what kind of job you are looking for, like if you are going for a designer, then you should do some at least write some good amount of design hardware using Verilog, and then you maintain your own repository that these all designs I have done, and then when you apply for a designer role, then obviously they will consider. If you are looking for, then other than designer, if you are going for a say for synthesis, say for floor plan, if you are going, then you should be aware of the concepts, at least what is happening inside that. If you have done any hands-on right now, the government is giving free tools, free EDA tools to most of the institutes. Major institutes have got the tools. So using those tools, if you are able to uh, mm, learn the entire flow, and you can add that as that part as your in your resume, and then you can pitch to those kind of job vacancies.
Sir, is there any
Depend-
open source media tools are there?
Yeah, open source EDA tools are there, but they are not up to the market. Ready. They are okay for learning, for a fresher to learn. That is fine, but those are not still completely as equivalent to as the commercial tools.
Okay, no maturity. It has not reached maturity.
Yeah, it has not evolved much. There are, see, these commercial tools are there for past some 30 to 40 years, and see the amount of evolution in the tools they would have gone through with the technological growth also. They would have added a lot of components in it. But open source are like we are like people as like us are working towards that, and we are pushing it, like we are also contributing it in that. But it cannot go to that level of uh, correctness that the commercial tools are giving it. Fine, that's all. Yeah, we'll go to this now. So we have completed RTL, and today's class also I was telling we were entering into synthesis. In synthesis, people go to the FPGA based synthesis as well as ASIC based synthesis. So as a company, what we will do is what the company will first see is I'll first get an FPGA board. First validate my design, whether my design is going to work as per the expected requirement in the hardware by itself. So if it is going to work inside the FPGA chip, and then further, then I'll be moving to the ASIC flow. Why? Because if I'm going to go to the ASIC flow, application specific integrated circuit flow, if I'm going to that, then I am going to pay an advance to the fab and book the fab slot, and then I am going to work towards that and then meet the deadline to the fab slot, and I am going to hand over it to the fab, which is a huge costly business. Okay, it is not going to be an affordable cost. It is going to be in crores. Okay, uh, to do the fabrication before the chip gets fabricated, I will have to ensure at every step whether my chip is going to work correctly. If in any situation it should not fail. Okay, for that the first step as a designer, what they will do is first they will dump the RTL whatever they have written inside an FPGA chip, which is an affordable. It will be in few thousands, that FPGA boards. You dump inside that FPGA board, you emulate your design through the hardware. You again see, you write a test bench and pass those values inside the FPGA board and see whether your design is working as per the requirement on the FPGA. So this will ensure, this will make sure that you will get you once you take this design, your design will behave as it is behaving inside an FPGA. So there is, yeah, now you have another team, FPGA team, where you will have, where that team will be taking the RTL from the designer and it will be implementing inside that FPGA and it will be verifying the design. So there is a team in a company for FPGA, and that is also another job vacancy will be there. Any doubt until now?
Sir, I have a doubt.
Yeah, Dhanush?
As you have said, like the FPGA team will FPGA which is not with lesser cost than the fabricated one,
Yes,
and
FPGA.
implement the RTL.
No, I'm not getting clearly, Dhanush. Can you come again once again?
Hello.
Yeah, Dhanush, can you come again once again? What you're saying?
Yeah. Like my doubt is before fabricating the original FPGA, which is high, which will cost the cost of the FPGA will be high. You said that the team will run the RTL on a cheaper model of the FPGA board.
No. I am saying before fabricating your chip, that is going to be when you are going to fabricate the chip, it is going to be your own chip, your own silicon in hand. Okay.
Yes, sir.
Yeah, but FPGA is a chip by itself. In that FPGA chip, you are going to dump your design.
Yes, sir.
So once you are going to dump your design inside an FPGA chip, that means your design is translated to a real hardware. Now, if your design is able to work inside an FPGA chip as per the expected requirement, which gives me a confidence that I can take this RTL and then proceed it to the ASIC flow and then go to the fabrication unit for manufacturing.
Yeah, my doubt here is that FPGA which is already we are dumping the RTL in it, which is already a pre-built one which is available. Am I right?
Yes.
Yeah, but will that give the 100% of outcome which you are expecting from the RTL scheme than the fabricated one?
No, it is not going to give you 100%, but I'm saying at least it will be functionally verified. It will be functionally whether it is working or not, that you will be able to see. But performance wise, if you are asking performance wise, that then it will not be suiting you. That's the point of that's the point of fabricating your own chip. If you're going to fabricate your own chip, then it will give it will give you a better performance. In FPGA, you are just validating the functionality of the design. Whether if my design is put into if my design is going to come as a hardware, whether it is going to work correctly as per the requirement or not. That's the only validation you are doing.
Okay.
Pavitran is asking something. ASIC designers first implement the design on an FPGA, and once the functionality is verified and meets the expected outcome, they proceed with ASIC development. Sir. Yes, you are right, Pavitran. ASIC designer will not implement the design on FPGA. Rather, the designer will implement the design on an FPGA, and then FPGA there will be a team that will be helping for doing that. Then after once the design is verified in the FPGA, you can then the same RTL is hand over to the ASIC team. ASIC team is the team which takes care for the fabrication. Is that clear, Pavitra? Does that answer, Pavitra?
Yes, sir.
Okay. So Pavitran, to add to you, one more thing is, so suppose you are freezing, suppose you have seen that your design is properly working in the FPGA. And you feel that I mean, and your requirement is like it is not, your design is not very much performance aggressive. It is like if it is working itself, that is itself is fine. If that is your requirement, then you need not go for the ASIC development process at all. You can stop here itself. You can take the design along the FPGA, and you can use the FPGA board itself to for your application. For example, your application is like blinking an LED. You are going to toggle an LED after 5 seconds, every 5 seconds it has to toggle. Okay. Then your FPGA board will have an FPGA chip along with an LED. You will just dump your RTL inside that and see whether it is able to toggle an LED. Some ones and zeros to toggle. And if it is working, yeah, that is fine. My functionality is met, and I think that is in my FPGA board itself, I'm able to meet the functionality and it is working. Okay. And if you want to implement any other new design with the same board, we can reprogram it and see whether it is working for the new design. So this design iteration, whenever you are making new design and you are going to change and see whether it is working, all this could be done on an FPGA board. But if you are freezing the design and you are taking it for a dedicated chip, which is going to go through this ASIC flow, that is not going to, in that the design iteration will not go through. It will be like one design and it is going to tape out one specific chip for that. Got it?
Yes, sir.
Sir, can you repeat the second part, sir? Like once FPGA on the FPGA it is tested, you mentioned about async one, right?
Once you have verified your design in an FPGA, and see that you are meeting your functionality is met, but I wanted to implement on a separate chip my design.
Okay.
And in that case, then you will go with the ASIC flow.
Async flow.
Yeah, this
ASIC flow. Oh,
ASIC flow.
ASIC.
Yeah,
Okay.
ASIC flow.
Okay. Okay. Because on ASIC flow you cannot change anything, right? Once it is freezed, then only you can go with ASIC, correct?
Yes. Once your RTL is freezed, then you take that design and the entire flow it goes, and then that will go for the manufacturing. But in FPGA, it will not be that way. FPGA, you can reprogram it again and again and see.
Okay, I think for every ASIC thing flow, before that FPGA will come into picture, right?
Exactly. That's what I was trying to tell you, like for the past 10 minutes.
Okay, okay. It's a kind of a sandbox or a test board.
Yes, yes.
And sometimes that also can be used in real time, is what you were saying in some scenarios.
Yeah, that can be taken because if you're not able to invest huge money for the tape out, giving it to the fabrication unit, and your design is also not required, like it is not very much performance aggressive also, then you can stop it in FPGA itself, and you can take that and bring it as a product by itself.
Okay, okay. But it may not be that much compatible in small devices and all, right?
Then you have to customize that FPGA board, FPGA chip, what you are getting. No, you have to get the FPGA chip, bring your own board, customized board that is required for you. Then you can do that. Even then, if it is not working, then there is no choice. You have to go to ASIC only.
Yes, I see only.
Yeah.
Okay. Okay.
So ASIC is called ASIC, sir. We usually say
Okay.
colloquially
ASIC.
ASIC. Yeah.
Okay. ASIC. Okay. Okay.
Yeah.
Okay. Okay. Thank you, sir.
Yeah.
Okay, sir. Suppose if there are different variants for a chip, then in that case, in the ASIC flow, where it will be fabricated on different dies, or like it's like on the same only, and depending on each customer's requirement, they will be using that.
Exactly. Your question itself has an answer. So if you are having different components that has to be handled separately, then it has to go on a different chip.
Okay.
Yeah, I had a question. So this FPGA chips, right? So they will have the same PPA characteristics, or they should have as the actual die that we want to produce, right? Or is it
No, you will not have the same
no
PPA
case?
characteristics.
Yeah. So for example, the actual chip might have a very small area. So when we uh, prototype it on a FPGA, shouldn't it also have the same type of area and other characteristics, the power and the performance characteristics?
No, you will not have the same area, same power, same performance in FPGA. It is bound, whatever that FPGA chip has, the components are there. No, those are also transistors only. It will be the FPGA chips performance, FPGA chips area, and FPGA chips power will be there for your design. Your design actual area, power, performance will be only seen once it has become a dedicated chip. It is not
Okay.
yeah, in FPGA it will be the FPGA chips performance, FPGA chips area, that will be there.
Okay.
Sir,
Yeah.
hello. Sir, if anybody who wants to switch from web development domain to Velisai, sir, is it,
I mean, is it you're asking for yourself or somebody else?
sir, somebody else?
Okay. Those are two totally orthogonally different domains, Marufa. So it is depends on their interest and their time for this. So can we use Linux OS on VirtualBox and all applications would be used? Yeah, you can do that, Sarthak. You can do if it's yeah, you can do that. Okay, so I think it's time. If you want me to spend some more time also, I can spend. But you can tell me if there is any other doubts.
Sir, in this design flow, what are the blocks that the PG design and IO ring design? Could you tell about that?
Which the PG design and IO ring design, yeah, that will be part of this course only. Once we come to this topic, I'll tell you. Or you want me to tell what is that? Means you will not understand. Basically, it is like once you finish your floor plan, you will understand what is a PG design is.
Okay, sir.
Okay, maybe I can tell you this. What is it like? See, inside the chip that you are going to design, right? It has to, for all the components in the design, it has to get proper power. It has to get proper supply. So for giving supply to all the components of the design, the power source should be available at all the places. It's very similar to like this. If you are going to construct a new house, okay, once you have constructed, then you will have to install the power switches, right, at every places. Like if you want to, if you're at your bedroom and you wanted to have a power switch for your fan, for your AC, for everything, then you will make sure that it just lies beside your beside the cot that you are going to sleep, right? So you will have to ensure sufficient power and the required power goes to every places in your design. Like that, you have to ensure. That is the power grid design.
Okay.
Yeah. Anything else?
That's it.
Okay, fine. Then let's wind off today. We'll see. At every phase of the class, I will bring this picture, and then show you some, like whenever we are progressing, I should bring this picture and tell you.
This recording will be available immediately, sir. Some details.
I'm not sure about that. I think physics wala you will
Okay.
have to check.
Okay, sir.
Okay.
Satya, recorded will be uploaded maybe 27 because tomorrow will be off. Okay. If we will upload, we will inform you accordingly. Okay.
And
Yes.
Satya sir, actually in the starting of the class itself, I was checking for you because when I started you, if you are late, then you will ask once again. No, so I checked for you also.
Yes,
Whether
sir.
Satya
Today
is
I
there.
am really sorry because today is an auspicious day. There was some pujas going on. I
Okay.
joined after that actually, just a little late actually. Yeah.
No issues, no issues. I just checked for you whether you were available in the class initially.
Yeah. So if if the support people can upload a little earlier, we can go through this recording again. It will be helpful for us to revise.
Sure, we will
Both
try. Okay.
languages. Yeah.
Okay. Thank you.
Okay, yeah. Thank you.
Thank you.
Thank
Thank
you,
you.
sir.
Thank you,
Bye.
sir.
Bye.
Thank you, sir.
Thank you, sir.
Bye. Thank you.
Thank you.
Thank you, sir.
Thank you. Bye. Thank you, Satya. Hello, everyone. Good evening.
Good evening, sir.
Good evening. Yeah.
Good evening, sir.
Good evening, sir.
Yeah. Thank you.
Good
We'll
evening,
start.
sir.
Yeah. Good evening. We'll start. Okay. So one announcement, wanted to make it before the class itself. So this week I was not able to give you the questions and for the exam because I was not well. I'm still not well, but wanted to complete the syllabus. So I'm coming for the class alone now. So I by next Wednesday, the exams will be there. I will share the questions with the physics wala team. They will upload and let you know. So sorry for that. Last week I was not able to give you the questions.
So, no, sorry, sir. You are attending the class with even with sickness also. That itself is great. You should have taken rest.
No, but then we will miss out the timeline for this class. So that's not good. So let's. I mean, I'm okay. I mean, I can handle, but for 1.5 hours, so it's fine. In between, I'll take some 2 minutes break. That's all.
No problem, sir. It's up to you.
Yeah. Mm. Okay. So coming back, yes, last class we were discussing about uh, synthesis, the two types of synthesis that happens. One is FPGA based synthesis, another one is an ASIC based synthesis. And any doubts until now? Because right now we are going to enter into the core part of the VLSI design, where you are going to see how these days the chips are implemented, how your Verilog written Verilog gets translated to silicon. We are going to right now enter into that. So any doubts until that, we'll spend some 5 minutes now for that. Any doubts, any clarifications, we will handle it now itself. Were you able to look into the recording, Satya, last time when because you joined late?
Uh, yes, sir. Up to some extent, still it is some more thing is pending. Actually, I'll go through them. Actually,
Fine.
yeah.
Any doubts? If you have, we'll take it up. Others?
Sir, we are discussed about the software as last class. I very low.
Yeah.
I actually my doubt is that I'm using MacBook Pro. So in that Mac we can install that I very low.
Yeah, I think it's available for all operating system, Ramya.
Okay. Can you show how we work with that once more? My doubt is that we doing that code in terminals.
So that one you will have to just take the help of ChatGPT, whatever I mean, this is all completely Linux things that you have to take it up. But what I would say is when we go to hands-on, with later part of the session when we are going for a hands-on, by then you should be able to at least work a bit on Linux since you know Mac. In Mac, you will be able to see terminal, right? In terminal, you
Yeah.
will be accessing it. So how do you open up a text file? How do you edit the text?
Because like weekdays have full day college.
Yeah, it is 10 minutes only.
Yes, sir. Like what time of the day, sir?
Uh, how is that done? I don't know, but from physics wala team, like, is there any specific time from for the exams physics wala team? Or how is it given to the participants?
Sir,
Last time,
as per the exam policies, we conduct exam in early morning, like 9 a.m. to 9:10 a.m. And if any urgency, we only schedule 9 to 10. We schedule exam between 9 to 10 a.m.
Okay, so that way it will be given, Jayvardhan.
So it will
Yeah,
be
right.
coming Sunday. Tomorrow exam is there.
No, I am saying I am trying to schedule it on Wednesday.
Okay.
Yeah.
Think so. I might have practicals during that time, sir. Like 9 to
Yeah, it's a working day, so it will be a bit difficult for me also.
We
Fine.
Yeah,
I
Sunday
will
will
give.
be better.
we can plan on next Saturday before starting the class. We can take the exam and start the class, right, sir?
Yeah, I think I'll leave this to physics wala team. Let them decide. For me, before the last class, whenever it is possible, complete the exam and come in.
Uh,
So yeah, tell me physics wala team. You mentioned.
we try to schedule on Saturday.
Yeah.
Fine. Okay, then that should work for everyone.
Yes, sir.
Okay, okay, sir.
Thank you, sir.
It is
And
just a
further
10. Yeah. It,
further informations we will let you through email or WhatsApp community.
Okay.
Okay, sir.
it is going to be just 10 minutes. It will not be more than that. So plan accordingly on Saturday.
or otherwise, can you schedule a night time? Wednesday night, it's possible, just for 10 minutes.
No, Saturday is better.
Saturday is better.
Okay, let's not discuss here. Let's come to the class. We have only 1.5 hours time. Physics wala team will let you know. Okay, Saturday should be better, I think. Okay. So any doubts? I was asking that. Any doubts? Anirudh, Jayvardhan, whoever is usually asking me doubts. Any doubts until now?
For
Fine.
now, no, sir.
Okay. Okay. So yeah. Anyone tell me what is synthesis is? Anirudh? Yeah. Yeah, you are unmuted. What is synthesis? Okay, leave Anirudh. Anyone else?
Sir, I think synthesis is SDL code convert to netlist hardware language.
Good, good. Pavitran has said like converts the RTL code into real hardware. Yes, somewhat whatever you're saying is right. Part of your answer is right. Okay, good. Anirudh, gate level nest list of Verilog code. Good. So I from your answers I get that you know what is you heard of what is netlist is, what is gate level netlist. I think you are aware of it. Okay, let's considering the other participants also in the class. Let me tell you what the terminologies that is there in this. Let me start with the terminologies. Okay. Okay, I think you are able to see my screen.
Yes, sir.
Yes, sir.
Yes, okay. Okay, so synthesis. Yeah. So synthesis is a process of converting the RTL code, which is written in Verilog, slash system Verilog slash dospec system Verilog in any of the hardware language is converted to RTL will get converted to gate level netlist. So what is gate level netlist is so this is a process where with the help of the EDA tool, with the help of these EDA tools like tools like Synopsys and Cadence, your RTL is given as input to the synthesizing tool, and it gives you an optimized netlist. So other than your RTL, there are few other things which are given as an input, which will generate this netlist. One is your technology library. Okay, let's see what this technology library means. So once you have decided that your RTL, your Verilog code that you have written, say for a processor you have written, That Verilog code is uh, mm, will has to be has to be has to go through the process for fabrication. So you have to decide on which foundry node you are going to fabricate it. Say TSMC 40 nanometer or TSMC 8 nanometer, or you have Global Foundry, say 22 nanometer. You have our own. In our country, we have SCL, that is Semiconductor Laboratories at Chandigarh, SCL Chandigarh, which has 180 nanometer technology node. So these are the uh, technology part. So I hope everyone knows what this 180 nanometer, 22 nanometer, 8 nanometer, 40 nanometer translates into what does value mean on a transistor. Everybody is aware of it? Anybody has any doubts in that?
Channel length, right?
Come again?
Is it channel length?
Yes, it's the gate, the channel is there, no? The gate length or the channel length.
Yeah.
Yeah. Anybody has any doubt in this? We'll proceed with this. Anyone want to know what is it?
So
Sir,
TSMC
SCL is
you
180
mentioned.
nanometer.
Yeah, SAL is 180 nanometer. Yeah, Satya sir?
Sir, you are saying this TSMC, right?
Yeah.
TSMC is also channel length.
No. Okay. These are fabs. These are different fab. TSMC is
Okay,
from
okay,
Taiwan.
okay. Got you. These are the different nodes from different companies, right?
Different nodes from different companies. Correct.
Depending upon our intention of what size of the chip
Chip is
to be
depend. Yeah.
manufactured.
Yes.
Okay,
Depending upon your requirement, you can choose that.
okay.
So
And
I mean to ask the
just I'm
question
also
is.
mapping, sir. Earlier you have drawn the flow diagram, I think 2 to 3 classes before, right? Exactly, this will come before the system integration only.
Can someone mute that? Like who was it in between?
This step exactly comes at that SOC, right? Where the PCB is generated before the system integration, correct?
No, this steps. Which one you're saying? Synthesis?
Yes, this RTL, going through this synthesis framework or library to generate the
So
netlist.
this comes after once your specification is ready.
Okay.
And once you read the specification, then you go for writing your hardware. That's your RTL.
Okay, hardware portion of the specification, right?
Yeah, hardware. The digital hardware portion of the specification.
Okay, because after hardware you have the IC design and fabrication, right?
Yeah, right now we are into IC design process only. How the first step for IC design process is synthesis.
Okay, where the RTL code is converted through this to netlist.
Yeah, the process of converting your RTL to netlist is called synthesis.
Synthesis using these tools, like.
Yeah,
Right.
using the EDA tools like Synopsys and Cadence.
And one more thing you mentioned, sir, like because if we write the code, and it will take a huge time, right, for these, because you have billions and millions of transistors and all, right? That's where we are using these Synopsys EDA tools, correct?
Yeah.
Right. Please correct me if I'm wrong, sir.
Yeah. So I'll come to that. Actually,
Okay, sorry. Okay.
that needs a little more explanation. I'll come to that.
Okay. I'm just mapping with the previous sessions. Okay.
Yeah.
Sorry.
So let's come to this. So my question was like, are you guys aware of what is 40 nanometer, what is 8 nanometer, 22 nanometer, and 180 nanometer? So basically, it is if your transistor is you have a MOS, right? You have a PMOS and NMOS. So it'll have source, drain, and gate. So this is the channel length that is defined as 180 nanometer for SCL Chandigarh, and for Global Foundry you have 22 nanometer. You have again 45. There are a lot of other technology nodes which I have not mentioned. I just gave you some examples. Okay, now from the fab, so we are right now talking about this technology library that has to be given as input for the synthesis tool. Okay, in the technology, for this technology library only, you will have to basically have an NDA. NDA is called non-disclosure agreement between you and the fab. Between NDA is between you and the fab, and then the fab will give you will share you a technology library files which are required for doing synthesis. So what are those technology library files actually mean is, they those the technology library will will comprises of so it's called process development kit. It's called PDK. These terms are very, very important. So please pay attention. These are some fundamental terms which I will be taking up again and again in this class. I don't want someone to ask again what is PDK, what is it? I really don't know. No, nothing like that. Please. Please pay attention. So this process development kit is provided by the technology partner. It can be TSMC, Global Foundry, anyone who is doing fabrication. They will give you a set of library files that will be taken by they can be that is taken as an input by the EDA tools. Okay, so what does this process development PDK consist of? One, it consists of standard cells. So these are all normal text files in different formats. Okay, so standard cells are usually given in .lib format, or it is given at .db format. Both are same, but the file format is different. Like it will be an extension of .lib, or it is an extension of .db. Okay, what does the standard cells has? Standard cells. What does standard cells means? So as the name says, standard means there are certain aspects of the cells which are kept as standard, like the cell's height. The height of the cell is is constant for any cells. Say standard cells comprises of like and, or, nor, flip-flops, XOR, like etc. Okay. For all these cells, if you see, the height of the cell remains the same. Like what does cell's height means is, in the standard cell, so I mean, I think everybody is aware of the layout of an inverter. Are you guys aware of the layout of an inverter? Which I mean, was it shown earlier to you?
No, sir, I think.
Okay, fine.
Sir, CMOS inverter or anything else?
Eh, I mean, CMOS inverters layout. Any layout was shown to you? How does the
No,
layout looks like?
Uma ma'am, brief,
Yeah,
small.
yeah, that's what I'm asking. I think she was telling. She told.
Yes,
okay. Okay.
yes, sir.
CMOS has been described, sir. CMOS is
It was
been.
in one of the slides.
Okay.
I think that was shown. Yeah.
Okay, is Uma ma'am on the call? I think she's not there today. Okay. Yeah, I think I remember she was showing you about how does a inverter layout looks like. The color diagram. Maybe I'll show you somewhere where do I have. Uh,
Yes, sir.
Yes.
Yeah, so this is something that I have searched online immediately for you. So this is a CMOS inverter, as everyone knows it. So the right one, which is given in color diagram. Okay, so this is the layout implementation. This is how finally your inverter looks like inside your chip during fabrication. This is how the fabrication is done. So I request everyone to go look into this. These are like there in the Maurice Mano book itself. Like it will tell you about the stick diagrams. It's called stick diagrams. Usually, the undergraduate people, students, when they study about this, they draw this for inverter, NAND gate, everything. So here, if you see, this is called the cell height, like the bot from here to bottom to top for an inverter, the height is this much from the bottom to top is the cell height. Okay, this cell height remains same for any of the cells that is there in the part of library, that is part of the library. So that is what I was trying to explain. Okay. I hope you guys got what is the, I mean, looking into the layout. Do you, are you guys, I hope you guys got what is this layout of inverter looks like.
So the bigger ones are also cells, sir. The ones that are shown, the bigger ones in the middle.
This is completely one cell for
One cell.
inverter.
Oh, okay. Well, this is completely one cell. From top
Yeah,
to bottom is the height. Okay.
yeah, yes.
Okay.
So when you draw layout like this for implementing an inverter, actually, actual process starts like this only. Somebody wanted to do fabrication in a particular technology. They start to draw layout like this for each cell, like starting from an inverter to AND gate, everything. They start drawing this layout, and through this layout only then it is so when you start drawing the layout, it is called full custom design. So full custom is nothing but you start drawing layout for, say you have written a code for counter, and when right now you started writing from the count for from like started writing Verilog code for counter. But previously those days were not like that. Nobody was writing code. Those days they started with drawing layout only, like this only they started drawing. For counter you have D flip flop, suppose 4-bit counter is there, then you'll have 4 D flip flop and some logic gates will be there. So those logic gates, D flip flop, everything was drawn like this. Manually they draw, and this is a very it is this requires lot of skill set for you, because this there are certain rules that has to be followed for drawing this. So when you draw from the scratch, it's called full custom design, like where you start your process by drawing layout. And when you when people have already drawn for you, like for CMOS inverter, they have drawn this and freezed this. For AND gate, they have drawn some logic for layout, something like this, and they have freezed this. So at those point, what they will ensure is they will ensure the height of the cell to be same, for AND gate or anything. They will do all the gimmicks inside this place for implementing the AND logic or OR logic, anything, ensuring the height of the cell remains same. That is because when these cells come and sits inside the chip, so it will be easy for us to control the entire implementation. That's the intention of keeping the height of the cell as same for that particular technology. So here, if you see the high the I mean, so that is why that's called semi-custom, where you you use the cells that is already given by the fab. Those are already designed by them. You are using it, you're just taking them as a part of library and using it. And this aspect of designing cells, okay, of designing and implementing your design, has given a big leverage for the engineers, for the industry to like design quickly. The design time is completely reduced, the implementation time is completely reduced because of this, because these are like libraries available. You just pick, the tool will pick from this and implement into your design. Whatever you have written will get, you'll be able to implement it. If this is not there, so what you will have to do, then you will have to draw this layout layer by layer. You will have to draw, then you have to implement this. I hope you guys are clear on what I'm saying. It any doubts?
So in a way, the library encapsulates the entire architecture of this complete this thing, inverter circuit or whatever.
Library will encapsulate all the required cells that will be taken by your design, to and that will get implemented.
Okay. Okay.
Any doubts? Any other doubts, guys?
Sir,
So
every time there will be a different, like for every design, it will be different, or it will be like a standard one, which will be encapsulating that.
The technology library will be going to be one standard thing. Depending upon your design, the EDA tool will pick the required cells. That is, suppose your design has a AND logic, or your RTL has an AND logic, it will go and pick the AND cell from the library. So your design, depending upon your design, that is not going to change. I hope you are clear, Smita.
Yeah, yes. And okay, the technology node also, like, that will also be taken into account, right? While doing this
Yeah,
PDK.
that's what I started my class with that.
Yes, 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 yes. Okay, thank you.
Sir, design standard, whatever you're saying, this architecture, it is like TOGAF standard, similar type of, or a SOSA standard, similar type of things.
Come again?
So, whatever the architecture will be designing, through which we have to follow these standards,
Huh.
however shown, that like TOGAF standard or SOSA standard, it is like this.
No, I'm not still getting your question. What standard you are saying? I'm not getting it.
TOGAF, the Open Group Foundation, or SOSA, SOSA is the sensor open system architecture.
No, I'm not getting your question at all. Like what standard I mean, this is for writing RTL you are saying, or?
Known as designing, for the design purpose,
Yeah,
whatever
design
this
is RTL.
specific. No, however you show as the design of the cell height, whenever we do this architecture and design,
Okay.
it will be similar to that one, the SOSA standard. SOSA is the one of the architecture for this drone and this thing that is called sensor open system architecture, it is used for the automotive sector.
Okay, fine. So I got your question now. What I'm saying is, so this is for the chip design that you are going to take it for implementation. It's not for your product like drone and all. That will have its own standard. For doing your chip design, it will, if there is any standard implementations required for designing the chip, that will also come into account. For example, if you're going to design a chip for your automotive grade, like for say you are going to design it for your for a car, so there are some certifications called functional safety certification, FUSA, that's called FUSA. Those are and all will come into account, and your design has to accommodate all those standards, and that RTL at the level of writing Verilog code itself, that has to be abided. So this is not for product. What I'm saying, I'm talking about designing a chip, and for that designing a chip at RTL level, if there is any standard metrics are there, that has to be avoided.
Okay, sir.
Okay. So I hope you guys are clear until now. Now, so we were talking about the standard cells. For standard cells, yeah, the cell height has to be constant. That's what I was telling. 1 minute. So what is actually the height has to be constant. So what about the width? Width is like something that can be variable width. So if you are able to vary the so I request everyone to see, like can Google and see for inverter how the as I showed you, how does the layout looks like. Similarly, you can look for some other gates also. So only the height will remain constant. The width will be in a variable state, like where you can implement your and design in the layout. Okay. Uh, so why what are they going to achieve by doing this, by keeping this is, so what will the tool will do is, first thing when you are when you are going to mm, use the cells in your design, say this is your chip, okay, and in the chip you will have something called as site rows, okay, like this. After synthesis, when you are going to place all the standard cells inside the chip, when you are going to make a chip, so at that time these cells will come and sit like this. So here if you see, the cells height will be same, but it can be in a different size. So this will help us. So this is basically will help us to accommodate all the cells. So this will be all the placement of these all cells will be done using EDA tools only. So the tool will take care in placing the cells. This will make the work of the EDA tool easy. So coming back to this, so the PDK, which is process development kit, that is given by the technology fab, there that will comprise of one standard cells. What are those standard cells? You have and, or, nor, all the combinational and sequential part of the hardware element. Second, you will have macros. So macros also will be given in the form of .lib and .db. So what are macros? Macros will comprise of SRAM, DRAM, ROM. So these are some huge chunks of memory that will be given by the fab to you for using it in case you have in your design you have iCache, Dcache, you have tightly coupled memories, etc. And suppose you have ROMs in your design. These has to be at when you're writing your Verilog code, you would have written it in the Verilog code for iCache, Dcache, everything. But actually, when you want to implement iCache and Dcache on a chip that require this SRAM, DRAM, you can't go use the flip-flops instead of that, because that will bloat up the chip. That will have huge area when you are going to use flip-flops. This that will consume huge area. Like if you are aware of the caches, about caches, you have one R, one W, which is called one read, one write, and one RW is called one read write. That means you have separate time for reading and separate time for writing. Like once you are reading, you can as well write. This means you can either read or write at once. So, I mean, what does this mean is suppose this is your SRAM, and you have what is the size of the exam is? The SRAM is 32 cross 32. That means you have 32 bits of address bus and 32 bits of data bus. So this is the size of the SRAM. So this will be provided by the fab itself. So then your PDK comprises of standard cells, macros, and then you have IO cells. IO cells are IO cells are the one that is left over. So suppose your design, your whatever Verilog code you have written, if I'm trying to put inside the chip, so I will have all AND gates, NOR gates, your XOR gates, flip flops, everything. Sorry, heights will be same, right? So everything. And then you have macros, big chunks of memories, SRAMs. Other than that, you have the inputs and output pins. Okay, so if you remember, I was telling you when writing Verilog code, right? When you're going to write the Verilog code, you started with a module, then you declared all the inputs and outputs, then then your logic, then end module. Say this module name is an example, is the module name. So this is what. So what does this example means? This is the module name. This entire chip is the module name. Your inputs and outputs are these pins. Okay. Now, and whatever logic you have written here, that will come inside this. I hope everyone is clear. Any doubts? Guys, acknowledge no, I am feeling really
Yes, sir.
sure.
Yes.
Yes, sir.
Clear.
Yeah.
Then after that, we have written some behavioral thing and structural behavior in this one, right?
Yeah. Whatever you
Yeah.
have written between the
Yeah.
outputs and whatever before
And
end module
module.
is there, yeah, it will come
Yes.
inside this.
Yes. We call this from test bench.
Yeah. Test bench is something that will be used to pass inputs and outputs to your module, correct?
Yes, sir. We call
Yeah.
this from the test
Yes.
bench. Yeah.
Yeah. So what is actually in real time in the chip test bench means is you pass inputs through the pins of this your chip. That is the test bench. Okay. Test bench doesn't come as part of your chip. Test bench is something that is once this chip comes out, then through these inputs and output ports that is module inside your test bench and pass value to the inputs and input pins of this module, and absorb the value at the output pin. That's what you do on a test bench, right? So that is what is in real time. The test bench is your real stimulus values that goes inside the chip. Okay. So what was pending inside in this was these IO cells that I was trying to explain. Apart from your standard cells, macros, there are IO cells. IO cells are cells that will be mapped with your inputs and output pins that is there. For example, you have inputs as A, B, C as input and D as output. Then, for example, A, B, C, and D. Then these pins are connected to the standard cells, the IO cells that are provided by the fabrication unit, that is a fab. So these are like IO pad cells will be available. These are called IO pad cells. There will be different IO pad cells available. Like you have in SRAM, macros, you have SRAM, DRAM, ROM, and standard cells, you have various different gates. For IO cells, you will have input pad cells, then you have output pad cells, then you have IO cells. IOs are like input and output, it could be configured in any way. Then you have And then you have clock pad cells where you give your clock signal through this clock pad cells. Yeah, it goes like this. So to summarize whatever I said now, I'm summarizing it. Please listen. So right now, what we were trying to do is we were trying to understand the synthesis process. Synthesis process is converting your RTL to netlist. Netlist is like gate level netlist. So for doing synthesis, one of the input is your RTL. Second input is going to be a technology library. Technology library only we were trying to explore. What does this technology library comprises of? So for that, we were going into the fab, different technology loads with different fabs. So all these fabs, if you're going to fabricate in any one of the fabs, so you will contact the fab. You will have an NDA disclosure, a non-disclosure agreement with the fab saying that I will not reveal anything about this, anything about the fab cells, anything, whatever you are going to provide is going to be within me. Then you go, the fab will give you once the NDA is complete, the fab will share with you a PDK kit, which is called Process Development Kit. This will kit will comprises of lot of files. In that, we are just seeing the library files, that is technology library files. In the technology library files, you have one as the standard cells. This comprises of and, or, and other combinational sequential cells. So I was saying about the cell height and the width, which could be variable. Cell height has to be constant for any particular technology node. So this holds only for the standard cells and doesn't hold anything upon the macros. Okay, macros height and width can be different. Um, so next we were seeing about macros. Macros are like SRAMs, DRAMs, and ROM. Which are like part of when you're when you're using a cache in your design, when you're having a tightly coupled memory, then you will be taking up all these cells that are provided by the technology partner, fab partner. Then the IO cells, which are like IO pad cells. Uh, these are cells that are used to connect the input and output pins of your design. These pins are connected through. I mean, are realized implemented through these IO pad cells. There are different IO pad cells. One is an input cell, output cell. Then you have IO cells and clock pad cells, etc. Any doubt? I have re-summarized everything. Any doubt?
Yes, sir, when you say connecting these cells, right, sir, the ports, right, that ABCD,
Yeah.
connecting to what, sir? Connection in between? I mean,
So
connecting to.
what does this connection? What does this mean? You tell answer this
Yeah,
question, sir. What does
which
this flip flop? What does this flip flop I have put inside this means? What does that mean? What does an AND gate that is there inside this mean?
yeah, we are
So
connected. Yeah, there the input ports are there. We are pins. We are passing the input through those pins, right?
no, no, hold on, sir, hold on. So
Yeah,
what I'm saying is in your RTL, in your Verilog code that you have written here, right?
yeah, yeah.
So in the Verilog code, you have your and gate, OR gate, flip flop, everything here, right?
Correct.
So this one you are taking, I mean this one the EDA tool picks and puts inside this,
Okay, okay,
correct?
okay.
And your
Yes.
leftover part are your inputs and outputs. For that, the translation of your RTL to netlist, for translating that you would require for input and output to has to be translated through this in IO pad cells.
Okay, okay,
Like your design, in your design you have and or, and that gets mapped with the with the library and gets implemented. Similarly for IO pad cells it gets implemented.
okay, okay. For the input and output.
Yes.
Okay, got it. And one more question, sir. The second step, right? We have the DRAM, SRAM, and all, right?
Yeah.
So internally they consist like within the DRAM or SRAM. They are like again a circuit like the flip flops and the inverters and all. Is a combination of that, or what it consists of actually internally?
Yes, yes. It has its own design strategy. Like I have shown you an inverter, right? How does that
Yeah,
look like?
yeah,
So
yeah.
similarly, they draw layout for SRAMs and DRAMs. There is a
Okay,
different set of logics that is required inside
okay,
that, that
got
is
it, sir.
implemented, but it is only for you. It will be given as one chunk of memory. You will not be given any access to look into inside that what is in what way it is implemented.
Yes, yes, into that layout, the like the
Yeah, yeah, yeah. That's why this is called semi-custom design. Whatever we are doing is a semi-custom design.
okay, 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 sir. Thank you.
Okay, guys, anyone else? I always hear
Sir,
it. Yeah.
sir, one more question. Like, you have told that .lib and .db are those technology libraries. So, what is the difference between both the, or like
Both
both
are
the?
same. Both are same. In .lib, if you open this file .lib, you will be able to see what is there. I'll show you how does the technology library looks like also. Okay, maybe by end of today class or maybe tomorrow morning class, I'll show you how does the .lib look like, and I'll also show you how do a .db looks like. .db is something that is not human readable. It will be like it is an encrypted form of .lib. That's all. Like for Synopsys only supports .db format. Like when you're doing synthesis in Synopsys design compiler, it takes only
Uh,
.db format. In
Okay.
Cadence Genes, it takes only .lib format. It doesn't take .db format. It is for the usage of tool point. The fab is providing that.
Okay, sir. So, is there any standardization imposed on this tools also, like, or they can follow any of this? Like just now you have
Yeah,
told
they
that.
the tool and the fab has to go hand in hand. For the tool they require certain format of the files and that has to be given by the fab. So they have a mutual understanding between both of them.
Okay. Thank you, sir.
Yeah. I always hear it from Smita or Satya sir or anyone else. Please go ahead because see when you open up, then only you will learn. Otherwise, it's the point of this class is goes useless. So please, anyone has any misunderstanding of whatever I have said, please open up.
I have doubts, sir.
Yeah, Jayvardhan, good.
Sir, about the macros, sir, like these SRAM slices, they usually need some overhead, right, sir? A controller type of row or column multiplexer to organize memory. Is it
Yes.
included in the macro or is it like externally in other cell?
No, no, those are aspects of SRAMs only. Right? The designing of SRAM requires all those things. So that means those are included inside the SRAM design itself.
Got it, sir. So
Okay.
like they're not external
No, no,
modules.
those are we are not going to work on that. We are just going to use the functionality of SRAM.
Got it, sir.
Okay. Anyone else? Good question, Jayvardhan. Yeah, Ramya.
So one down. If SRAM is 22 into 32 into 32 bar, that's the memory space.
Yeah, that
If
is the
we
size of
want,
the SRAM. Yeah,
yeah,
if you want a
more.
different configuration, the fab will provide you. Yeah, so that is given through something called as a memory compiler. It's called memory compiler. Again, it's a software that will be given to you from the fab, and you will be able to generate your own required memory cut
In that required chip.
for that chip. Yeah.
That means additional memory we can add it to.
Come again.
That means we can add the
That means
additional
whatever
memory.
you have and your RTL, right? What you're writing your design, no, in Verilog. At
Yeah.
that time itself, you know how much memory you
Memory
need.
we want. Yeah.
So you will generate the required memory using the memory compiler.
Okay.
Anyone else?
Sir,
Yeah, Pavitra.
sir, the layer diagram is derived from the Verilog code we define, right, sir?
The layout diagram, you're saying?
Sir, you have said that the SRAM in macros. So I'm asking that the layer diagram is derived from the Verilog code we define, sir.
Layer diagram, huh?
Layout diagram, sir.
The layout diagram, the one that I was showing for you in inverter.
Yes, sir, sir. In previous one.
Okay, those things are not derived from Verilog. Okay. So the layout is always done by the engineers who they draw the layout using the EDA tools. They draw the layout for inverter and gate, everything they draw, and that is being used as a standard cell that is used by us for our designs. Like whenever you are writing a Verilog code, and in your Verilog code, if an inverter is there, then for that the EDA tool will go and pick up this inverter and convert your RTL to a gate level netlist.
So the EDA tools makes us the layer diagram, sir.
Yeah, EDA tools will show you how does your design in your design what all gates are there. It will show you that these many gates are being used by your RTL, and it is going to pick those many hardware cells from the library. And in the library, yes, they would have implemented everything using the layout, and that will not be shown to you. That is kept as hidden only. It will not be shown to you.
Okay, sir. Thank you, sir.
Okay, good question. Anyone else? Marufa?
Yes, sir. I have a question.
Yeah.
Sir, actually, na, I want to know कि in these cells, sir, there is a combinational logic or sequential. Sir, in these
Um,
cells, like
y-
you draw in chips.
Here inside you're saying?
Sir, inside these chips, it's a matlab, I think it's yes, sir, yes, sir, yes, sir.
Inside this?
Inside this, like
Huh.
AND gates, OR gates, like combinational या फिर sequential circuit is
Yeah.
there.
Yeah, it is there. So why, as I told you, right? Inside in the Verilog code that you are writing here, this part of your design is there, no? That is before end module. Whatever is there, that will be that will comprise of combinational and sequential. A 1 minute break. Get some water and then we'll come back. Just 1 minute break. Guys, please recollect whatever I have taught. If any doubts is there, I mean, I understand that today whatever I'm teaching you is huge. There are a lot of things I am telling you today, but yeah, this is how it will be. It is going to be hereafter. So, any doubt is there, please clarify, or you can clarify tomorrow also. Just give me some time. Okay, guys. Come back. Okay, so I hope everybody is clear until now. Okay.
Sir, I have also one question.
Yeah.
Sir, can you give small practical example for this, all of this?
What
Like
practical example?
practical, like sir, anything like we have designing a chip, this will be used.
So these are some fundamental theoretical concepts you will have to understand first, Marufa. We will
Yes, sir.
show you, like I have taught you Verilog, and then I have shown you how do you simulate a Verilog code, like how do you write a Verilog code, and then after that I have
Yes,
showed you the waveform and all, right?
yes, sir.
Yeah, similarly, we will come to those part of the thing in the course. First, you please understand. I know that something these are like say, going to be some imagination in your mind. I know, but please understand. First of all, at least make sure you have the clarity. If you don't have clarity, let me know. I'll try to help you out that.
Okay, sir.
Yeah, hence coming about. I mean, I'll show you how does a. I mean, I know. I mean, you are aware like how does an RTL looks like. Is that clear? RTL, you know what is an RTL looks like? Marufa, it's for you.
Yes, yes, sir. Yes, sir.
Yeah, so your RTL, for example, you know about a counter code, like how counter Verilog code. So I will show you how does a netlist looks like. How does the after synthesis, how your RTL gets translated to your netlist. All those things I can show you. But before that, you need to understand what has gone through your RTL, what made your RTL in a netlist. How does that happen? That for that, you need to understand these basic fundamentals.
Okay, sir.
Okay.
Sir, one more thing. Whatever you teach in today, if that undergoes in the technology library,
Whatever I teach.
today topic that all are under the technology library. Comes under the technology library.
What technology library mean? What are you saying? I mean, in the course you are saying, huh?
Not code. Today we that means process development kits. Everything is come under the in between in inside the synthesis or
Yeah,
where.
it comes inside the synthesis.
Okay.
Now, what is your point? I still didn't get.
One more in diagram RTL in under technology technology library is there.
Yeah. So yeah,
That
whatever I have taught is part of this technology library that is going in for doing synthesis.
okay, okay.
Yeah, I have mentioned it multiple times.
I think we first we done the RTL, then we are going to the technology library.
Yeah.
Then after we go to synthesis. That's
No. So for doing the synthesis, you require in certain inputs. First is basic
okay,
your RTL, that is an input to doing
okay.
synthesis. Second is your technology library. So what is the technology library means? All those things only we were seeing it.
Okay, okay, okay. Thank you.
Yeah. Okay, no more confusions. I hope everybody is clear with that understanding. I'm moving forward. I will ask some questions in between. Be ready. I will pull out anyone in the class and ask. Be ready. Okay. So okay, guys. So we were writing. So if you remember, for in the Verilog code that you have written, okay, module. Say for counter, you have written some Verilog code. You have defined some inputs and outputs. Then you said always at the rate of pause edge clock q is equal to d. mm, then you do end module, begin and end, then you do end module. I'm just writing out roughly. Please don't mind if there is any syntax mistakes. So inputs A and clock uh, output reg B. Okay, so this is something for a simple counter that I was showing, right? Maybe maybe I'll show you the exact code that so I wanted somebody to answer. That's what I'm asking you. 1 minute. I'll just share my screen. Okay. So this is a Verilog code for counter. I hope everyone it's visible, right?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay.
Yes, sir.
So this whatever you are writing inside this, right? Always at the rate of passage of the clock. This will go inside the chip. Okay. This will go as the standard cells and flip-flops. This particular of logic that you are writing here will go as in the middle portion of the chip that I was saying. And this input and output, whatever you are writing here, this will go as your inputs and output IO pads. That will be a part of the, I mean, that will go as part of that in the chip. Okay. These will go as the standard cell part. Here, you don't have here in this design, you don't have macros and all. So this code that you have written will translate to that. You guys are, is that clear?
Yes, sir.
Okay, fine. So now just look into this code. Okay. All the inputs are here. If you see, input is clock and reset, output is count. Okay. Now I'll come back to this. I'll stop sharing it. So your inputs are clock and reset, and output is your count, which is 3 is to 0 count. Then passage of the clock. Then
Sir,
uh,
your screen is not visible.
oh, sorry. Okay. So this is going to be always at the rate of passage of clock. Then if you are if reset, then you have count be 0 0 0. You're initializing it. Then else uh count is going to be count plus 1 and so you have a begin here, begin and end module. So this is the code that you have written. And here, whatever you are writing, whatever you have, whatever is there inside this always and begin to end. This will go inside the actual chip part. So if this is your chip and these are having inputs and outputs. Yeah, I mean, I'm just drawing it, but actually, if you see here, what you have only clock and reset as the input, and you have only one output, which is going to be count, and all the other part that is there, this will get mapped inside this as standard cells. Got it?
Yes, sir.
Yes, sir.
Okay.
This
Now,
example maps well, actually. Yeah.
yeah, this exams map. I mean, I was just trying to bring this to you. Yeah. Now, yes, we'll go to this part which we were looking at here. Okay.
Sir, I have a doubt, sir.
Yeah, Jayavardhan.
Sir, if we write any like RTL, multiple combinations of standard cells can perform the same operation, sir. So how does the compiler like how does the compiler optimize for one particular function, sir?
Come again. Your doubts is like more not clear. Can you come again once?
Yes, sir. Like if we take an RTL, like a complex
Okay.
RTL,
Like
many
complex RTL.
combinations of
I mean,
yes, sir.
let's be clear there. Complex RTL means?
Complex RTL means like not single function oriented,
Yeah, there
like
will be a lot of
all
functions. Yes, yes.
like a full decoder, for example.
Okay.
Like multiple combinations of the same standard cells can execute that cell. So how does the compiler filter out
That's the
isomers?
job of the compiler, Jayavardhan. That's why you need EDA tools. The EDA tool is very mature to handle it. Like if whatever tons of design standard, I mean tons of logic is there in your RTL. Like there are a lot of logic in your RTL. The EDA tool will ensure that everything gets mapped to a the equivalent standard cell, and that's how it is being done. That's the job of an EDA tool, synthesis tool.
Yes, sir. Like, but sometimes there's more than one viable solution, sir. More than one viable combination. So how does the compiler like choose between uh,
Yeah, it is
combinations?
the compiler means what? The EDA tool compiler you're saying?
Yes, sir.
The synthesizing tool compiler.
Yes, sir.
Yeah. So for that you will have to know what are the algorithms that is being implemented for designing the compiler. So the
Yes, sir. Like,
algorithm, yeah. So that is part of something called as CAD tools for VLSI. करके. There is a separate course for that where you study different types of algorithms that are used for identifying the design aspect and implementing it. So these and all will come in a different subject overall.
yes, sir.
Yeah. Yeah, I mean, and that's your question is very interesting. If you have this subject in you're graduated or still studying,
Still studying, sir.
which year you are now?
Second, sir.
Okay, then if you have CAD for VLSI, if there is any course for you that can be taken as an elective, please go ahead and take it. That will have all these aspects of how these tools are being designed, like how these tools are using, what kind of algorithms are are being used in the tools. All will be dealt in that subject.
Yes, sir. I looked to it.
Yeah,
Thank you so much, sir.
sure, sure. Okay, so what we have right now haven't I've seen is like the different inputs that are required for doing synthesis. First one is the RTL, second one is the technology library. Mm, so if these two goes inside, if these RTL and technology library goes inside this engine, the synthesis engine. I'm calling it as engine because it's actually an engine only. So if this goes into an EDA tool engine, like this synthesis is happening, what it will translate? here is it will translate to a netlist. Netlist is the gate level component of your design. Gate level components will be there inside whatever the corresponding RTL is there for whatever RTL you have written for that corresponding gate level components will be there. So that is called a netlist. So maybe I will show you a netlist. How does that look like? How does a netlist look like? Mm, and then close this class. There is please remember the synthesis topic is not yet complete. You have one more component that is part of synthesis as input, which is going to be what? Can anyone guess? Can anyone guess another input that is required for doing synthesis?
Power supply.
Sir, Boolean.
No, I mean, see what you are doing in synthesis. First, you have this question in your mind. What you are doing in synthesis, you are going to convert your written RTL to a gate level component. Whatever I have taught here in the PDK dot library, everything that is going to happen. RTL is going to get converted to a gate level netlist using the synthesis tool. So what other aspect is missing other than your RTL and technology library that goes as input to the synthesis tool? What else?
Grid
One more.
voltage. Grid voltage or threshold voltage like this. Gate voltage.
No.
Sir, FPGA board
Timing.
library.
FPGA, why is it coming here? We are not into FPGA, pa. Who is it? Who was that?
Sir, clock tree, sir. Sir, Jiban Roy.
Jiban. No, we are not into that, Jiban Roy. Jayvardhan, what was it?
Clock tree,
Clock.
sir.
Come again, Jayvardhan, I missed yours.
Clock tree, sir.
Clock tree, yeah?
Yes, sir.
No, you are only partly correct. Satya sir, you want to say something?
Timing constraints.
Who was that?
Any specifications or
Prudvik, sir.
design constraints or
Yeah,
design
somebody was saying,
specifications?
Satya sir, 1 minute. Somebody else was saying timing constraints. Who was that?
Prudvik, sir.
Good, Prithvik. Good, very good. Let's give a round of applause to Prithvik. Prithvik, I know that like rest of the people are like new. I mean, can you give your background a little bit? Like who? I mean, you are completed your graduation.
No, sir. I'm second year student.
Oh, great, Prithvik. Which college?
Triple IT.
Triple IT.
Bhagalpur.
Oh, great. Okay, that's called timing constraints, which we will talk about tomorrow. Okay,
Sir, I
timing
just know
constraints.
that like map. I know that's why.
Okay, I mean, see, I know that people, I mean, other people will not know, but timing constraints, when it's coming from a second year student, it is really overwhelming. Good, Pradeep. Okay, so we will talk about this timing constraints tomorrow. So what I am trying to and also there will be a little bit of more about the standard cell. What is there inside the standard cell? I'll show you. Uh, like I was telling, right? The PDK process development kit that is given by the fab. It comprises of standard cells, macros, and IO cells. How does the dot lib look like? How does a AND library looks like? How does an OR library looks like? Are you guys curious to look into it?
Yes, sir,
Yes,
definitely.
sir.
Yes, sir.
Yeah. So I'll show you tomorrow. Tomorrow's class, I'll try to show you how does it look like. So these are the files that are provided by the fab uh, through a process called characterization. They characterize the cells and then they give this information. That means if you are going to use this kind of information, this standard cell library from here, once your chip gets fabricated, it will do the required performance, required area, required timing, whatever is there. It will work on this aspect only. Karke. Those are some benchmark values. Those are given by the fab. Yeah, all these things we will look tomorrow. But now I'm going to show you how does a netlist look like. Okay, and then wind up the class. And if there is any doubt also, I'll clarify. I hope you are able to see my screen.
Yes, sir.
Yes, sir.
So once you are done with the synthesis, okay. Once you are done with the synthesis, the netlist, how does that netlist look like? Okay, so this is for a systolic array. Systolic array is another RTL design, another design where huge multiplications and all, if it is carried out, the systolic array is used. So this is for a synthesis that has happened for a systolic array RTL. I'll show you the netlist of that. Okay. Uh, I hope you are able to see.
Yes, sir.
Okay. So see, this is the netlist that is getting generated by the synthesis tool. So here I have used Synopsys Design Compiler. That's why it is saying here created by Synopsys Design Ultra in a wire load mode. The version of the tool. Then when did I create? When did this netlist got created? With the date, time, and everything it mentions. Okay. So this is how a netlist looks. So it is also it also looks like a, I mean, it is also a Verilog code only, but the Verilog code that you have written will not have any gate level components inside there, will not have any technology gate level components, but a netlist will have a technology gate level components. So here the top module is going to be systolic array. Yeah, this is the top module, systolic. One minute. Systolic array. See, I'm using a Vim editor. Vim is an editor that could be used to open up a file, edit it like your Microsoft Word. And so all these things, please, as I told you last class, I mean, couple of classes before, like please install Linux and start using it slowly, because once you come to hands-on, that will be going to be a painful thing for you. So please be I mean, competent with that. So this is a editor which we generally in industry they use. Okay. See, this is for a systolic array, and see the number of lines the netlist has. It's around 4,36,296 lines are there. Okay. And here, if you see whatever these it's mentioned here, right? These are different cells, standard cells, technology library standard cells. These are cells I have mapped using our semiconductor laboratory Chandigarh 180 nanometer technology. So these are cells available from the PDK. As the name says here, it is and or invert. And if you see, this is NOR, invert, and this is OR and invert, like that. And this is an AND gate, NAND gate. Okay. Other aspect, like what is this 2 1 D1 is? It's a two input, one output AND gate. Okay. Sorry, it's a 2 plus 1, 3 input and 1 output AND gate. And here if you see again it is same. This 2 plus 1 3 input, and the output is 1 1 output. So this is an AND or invert gate. And if you see inverter, obviously will have one input and one output.
And each cell is unique, or how is the naming convention?
So these cells are like this. If you see this INV inverter 0D1, this could be used at multiple places. So if above itself they
Okay.
have used, here also they have used. So these cells are used, but the instance, this is called the instance name of the cell. This is going to be unique. Like you have written a Verilog code module and end module, then you have written test bench. In test bench, you are instantiating the cell, right? Instantiating the module. So whenever you are instantiating the module, you give a instance name for the
It's
module,
like
right?
a combination is the primary key.
Yeah, you give an instance
Yes.
name for the module.
Shell
Similarly, here
and
you have the
instance both
instance name for
combination is the
the,
primary key.
yeah, here you have the instance name for this particular inverter. So these are picked from the library, standard cell library from the Fab PDK that they have given. So this is how a netlist look like. These things will not be there inside your RTL that you are writing. In RTL, you will have just if there's if there is an inverter logic, you will use accordingly. If you're writing a behavioral code, if you're writing a structural code, you will be writing at your. I mean, you will not be aware of um, the standard cells at all. Is this clear? Is this clear?
Sir, that means we using same inverter for different purpose. Like
Yeah, you are going to use same inverter that is required at your design level. This we are not going to choose. It is not in our luxury to choose which inverter I am going to take. It is the tool that is going to take up in under some constraints, under some restriction. The tool will only pick up this inverter that will be required for your design, and also for like and or invert any other logic. Yes, Satya sir, you want to say something?
Yeah, Corey sir. So earlier you have shown the example of that counter, right, in the diagram, where
Mm,
you have one input and there is an output, and in
mm.
between you have the cells and different cells.
Yeah,
Those cells definitely will be picked up by that library, right? That is
these
for
are
the
the
counter.
cells. These are the
These are
cells.
okay. Okay, these are all the cells. And this entire list is for what, sir? That is for counter, but this entire net list is for
Yeah, this I
which?
said no. This is for a systolic array. This is another design.
Oh, systolic array. Okay, 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 okay.
Yeah, and you see these are D flip flops. This DFCRQ is there. No, these are D flip flops.
Okay, and systolic array, what it does, sir? Just
It is just for somewhere you need huge multiplication, all those things.
okay, okay, matrix multiplications and all.
Yes, yes, yeah.
Okay.
So I said no, you have standard cells and then flip flops
Oh,
and all in here. So here, if you
okay.
see, these are the D flip flop that is being taken, and so these are the instance name for D flip flop. Okay, the D flip flop that is there, this is picked up from the standard cell, and the corresponding instance name for this particular logic is this one, and
Mm.
the connections are done here like this. Like whenever you are doing an module instantiation, how does you do the connection like that? These are the
Yeah, yeah,
pins. These are this
yeah,
dot
yeah,
D dot
yeah.
CT dot CDN dot Q
Right, right,
are the
right.
pins of the D flip flop that is there, this D flip flop, and
Mm.
the connections are done accordingly here. These are the connection as per the logic. It is done here.
Yeah. So whatever that you are showing, right? This is what we simulate from the test bench, the one single line, right?
Yeah. So that is
It's a,
inside your test
that is
bench you instantiate.
yeah, because that is for one thing, one only one for one kind of operation, one kind of device. This is for millions of devices or multiple devices. This entire thing will
Yeah.
generate,
Yeah. Yeah.
which is a systolic array consistent.
Yeah. Yeah.
Okay.
Any other doubt?
Sir, and then this like once we have got this format, it will be based on the algorithms, right, from the CAT. That were also, you were saying that also, right?
Yeah, using those algorithms only, this compiler will run and then do the synthesis.
Okay. Okay.
Any other doubts?
After this, like what is the next step, sir? Once this netlist is generated just at high level?
Yeah, after netlist is generated, then you actually take this netlist and do your floor planning, placement, routing, CTS, everything. That will come next by next classes. It will come.
Okay.
Sir, what is that histolic or systolic array? Can you show us again? That is.
It is a systolic array. SYSTOLLIC. Systolic array.
Yeah, just show us now. Where is that? Select ones, which is called systolic array.
Yeah.
Okay. Yes.
So these are the inputs and output pins for this systolic array. These many inputs and these many outputs are there. And each input, what is the size of the input is declared here. Output is declared here. So like this only. So it's a big design. It's a quite big design. Then the required wires for this. So these are all, I mean, while writing Verilog code, you will not write like why if you require wired and all. So basically your netlist is a structural implementation of your RTL where it have the gate level components. I repeat, your netlist is a structural implementation, structural level implementation, Verilog implementation of your RTL having the gate level components. I hope you understood this phrase that I said now. Okay. Any other doubts other than Satya sir, Smita, Biswajit, and usually people? Okay, I'll ask a question otherwise. If any doubt is not coming from any other participant, then I'll ask a question. Okay, let me ask a question now. Okay, let me ask to someone who is new. Okay, I take Tamanna Verma. Okay, Tamanna Verma, please unmute your mic. Tamanna Verma, can I unmute your mic? Yeah, Tamanna Verma. I wanted you to talk. Is that okay? You have some device issue? Okay. Okay, then I'll ask a question. Okay. Tell me. Oh, but you can answer in the chat. Okay. Tamanna, can you tell me what is a standard cell is? Quickly. Quickly, you have only 10 seconds. Yeah, these are pre-designed blocks. Okay. Good. Okay. Okay, next is for Harish. Harish, please unmute your mic. Harish. Harish, are you there? Guys, I want you to be please responsible. I mean, little bit responsible, no? If you're not there, not paying attention, then what is it in the class? Harish, are you there? Then what is the point of me teaching it with all like effort from my side? Harish, see, I'll note down all the people who are not responsive, then and that accordingly the mark will be also taken care. Like the certification involves everything. Harish, are you there? Okay. Okay. I request physics wala team, please take care of this because you're I mean mm, people are like kept on unmute and then not responsive also. Please take care physics wala. I request you to raise this at your team level also.
Sure, sir. We acknowledge you.
Yeah. Okay, let me go to one more person. Palle Vineet, can you unmute your mic? Okay, who can volunteer for a question?
Sir, I can
Sir, I am
volunteer.
ready.
Sir, I
Yeah,
can
Rohan.
volunteer.
Rohan, you have been talking to me. I want someone who is new. Who is it? Like
So
anyone?
Me.
I am ready.
Okay,
Sir,
Shravan.
me too.
Shravani
Shravan.
and Shravani and one more was
Alamin.
Alamin. Yeah, Alamin. I've been talking to you also. Shravani, I think you were the one who presented right last time.
Yes, sir, but it was not proper.
Yeah, I know. But other than that, other than
Okay.
Shravani, yeah, Shravani, I'll keep it for you. One question for you. But other than Shravani, Monisha, unmute your mic. Okay, Dinisha, unmute your mic.
Sir, can
Yeah,
you hear me?
yeah, I can hear you, Dinisha.
Hello, sir.
Yeah.
Yes, sir.
So this is the first time you're talking to me?
Like I previously asked some doubts the starting of the class.
Okay. So yeah, the question is for you, Dinisha. What does a PDK means?
It's a process development kit that we used to generate netlist sir, using
Okay.
our RTL code and
What does a PDK
technology
comprises
library.
of?
Uh,
What does a PDK comprises of, Dinisha?
Hello?
Yeah, I can hear you.
So it consists of that technology library, no, sir. As I said before.
Okay, yeah, that's right.
Yeah.
Thank you, Dinisha.
Thank you, sir.
Dinisha, you are like which year?
I'm final year, sir.
Okay, fine.
Yeah.
Okay, Shravani, this is for you. Okay. She was telling about the technology library that is there part of PDK. In the technology library, what are libraries are there?
Like standard cells, macros, and IO cells.
Okay, and how Verilog code gets mapped with all these components that is there. Yeah, okay, good, Shravani.
Thank you, sir.
Yeah. Fine. Okay, then it's already late. We are like 15 minutes extra that I have to. Tomorrow morning, yeah, we'll meet again. See, guys, my kind request, please, whoever is putting on mute and not paying attention, like this is going to be a high impact for this class. I request, please don't do that. It's a request I'm doing as a request. I'm not ordering also because this is not going to be useful for you. I know that you can watch the recording multiple times, but that is not going to solve the purpose because you will have instant doubts that will come into picture. So yeah, I request this. Please take this as consideration from my side. Okay. Any other question? Any other query? Last call.
Sir, I have, sir.
Jayvardhan, yeah.
Sir, can you give a preview of like tomorrow's class? Sir? Like, what will we learn in that timing constraints? Sir?
Yeah. Tomorrow we are going to take up timing constraints and use it.
Yes, sir. Like any preview as to what it is, sir?
Oh, timing constraint, you want to give a preview?
Yes, sir.
Okay, so your synthesis tool, no, what does it actually does your RTL to netlist, it generates a netlist and it generates, no. So while generating the netlist, you would require uh, your RTL to get an performance, like you wanted to meet a particular timing. Your design has to run for a particular frequency. Are you able to achieve that frequency? Are you able to achieve the required area? Are you able to achieve the required power? Those aspects are like the constraints that we will give it to the tool so that the tool will pick up that requirement from you and will tell you whether I'm able to meet the required timing or not.
Yes, sir. Like usually, like during fabrication, the transistor will have defects, right, sir? So the timing is not very deterministic per transistor.
No, it is deterministic. I'll tell you everything tomorrow.
Yes, sir.
Yeah, just stay with that eagerness, Jayvardhan. We'll come back.
Thank you, sir.
Yeah, Rohan sir, you wanted to say something? I see a text message from you.
Sir, I was a few minutes late, so I don't know if you had mentioned this. So we are supposed to have a quiz last Friday, right?
Yeah, I think I
I'm not
mentioned the starting of the class itself. You were
sure.
late,
I
I
was
think.
a few minutes late. So I
Yeah,
want
I said like
because
I was not. It's kind of a catalog for you can use those cells for your design.
so the PDK along with it will also consider additional files, right?
Yeah. We will discuss one
Like
by one slowly.
okay.
Yeah.
Okay.
Okay. Then. Yeah. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Sir,
Bye.
Bye.
sir,
Yeah. Tell me. Someone was calling. Ramya.
sir,
Who was it?
sir, I'm Nandita, sir.
Yeah, Nandita Balaji.
Sir, currently I'm in first year, sir, so I have faced little difficulties while listening this topic, sir. Could
Yeah.
you give any videos, sir?
No, Nandita, I told no, like for few people we have separately in before the starting of the class itself we have taken up one call, no, like we who were people with lot of like gap and people with who are like first years and all. This is going to this is going to be a little bit more for you, but I request you to study this Maurice Mano book, Digital Logic Design,
Okay,
and
sir.
that is the fundamental. That is there, then I think everybody will be able to understand it.
Yes.
Yeah,
Yes, sir.
please, you. That's what I have. I kept on telling. Please, at least now you take it up. Otherwise, this class is This course is going to be useless for you, Nandita. Please take it up then.
Okay, okay,
Sir,
sir.
could you please repeat the book name of the book, please?
I'm saying Ruhan. Ruhan was the person who asked me.
Yes, sir.
Yeah, Ruhan,
Sir,
I'm
could you
giving.
repeat the name of the book?
Yeah, it's called Maurice Mano. M-O-R-I-S. Maurice Mano. M-A-N-O.
Okay, sir. Thank you, sir.
Yeah, Ruhan, I'm hearing your voice first time, is it?
Yes, sir.
Okay, good. Okay. Yeah, I think Marufa has put in the chat also. Good, Marufa. Thanks for that. That's all. We'll wind it off. See you tomorrow. Okay, bye.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Bye.
Thank you,
Thank
sir.
you, sir.
Bye.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Bye.
Thank you and good night, sir.
Thank you, Jivan. Thank you. Bye. Good night. Hello, everyone. Good morning.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Okay. Yeah, we'll get started. Before that, I got some two doubts in the chat. Okay, Marufa, you asked, is there any sources where we can learn to use iVerilog on Linux for programming? Okay. Marufa, first thing that you have to do is you have to install Linux in your machine. If you have Windows, you should also, you have a lot of YouTube videos which will help you to install Linux on your machine. That could be done. Okay. And after installing Linux, it is if you ask ChatGPT to how do I install iVerilog inside my Linux, it will help you to install iVerilog. Okay, that is a step-by-step process. So once your iVerilog is installed, and that's all. You have to know how do you use a terminal in Linux, how to go into a directory, how do you access files in Linux through terminal. These things are some of the very basic things that even Google can help you with. So there is no structured way of like something that is available. If I understand it rightly, it will not be available. So this is how you have to go through. Marufa. Marufa, yeah, I didn't hear you. Okay. And from Devdeep Chatterjee, good morning, sir. Can you name some of the free playlist for learning Verilog in detail? Yeah. So anything you can choose, sir. Any YouTube video you can choose. It is not like not like any specific things and all that. But if I get to see something, then I will share with physics wala, which they can also share it. Maybe after the class, I will look into it. If there is any Verilog videos, YouTube videos are there for Verilog. But the best way to learn is read the Maurice Mano book. But do your hands-on, reading it, applying it, do the hands-on. That's what I would always prefer. But yeah, I'll send it to you, sir. Is that fine?
Yes,
This
sir.
was
Thank you.
yeah, okay. Ramya, okay. Alamin, good morning, sir. Sir, other than Verilog, system Verilog, which other language also we need to concentrate on learning like C, Python or other? Okay. See, I would say, since if you are a fresher, if you are new to this industry, I think stick on to one language for your RTL, either Verilog or VHDL. I would prefer Verilog because that's the one that is most commonly taken forward in industry. VHDL is also taken, but most commonly it is Verilog. So I would say learn one language and have the versatility of on in that. Then I would say on the software side, yeah, you can um, on the software side, yeah, you can choose whichever you wanted, like C, Python, anything. On the hardware side, yeah, only one thing you can refer. Yeah, I see Pridvik giving reply for Devdeep saying that NPTEL video for hardware modeling using, yeah, that from IIT Kharagpur, what those videos will be very sensible. You can take it up. If any other videos are there, I'll share. Okay, so let's get started. Yeah, so yesterday, four chats.
Good morning, sir.
Who was it, Satya?
Yes, sir. Good morning.
Yeah, good morning, Satya. Just now you joined?
No. I joined 5 minutes back almost.
Okay, fine. Let's get into it. So yesterday we were looking about how do you handle synthesis, how do you take up the RTL, and how through synthesis it gets converted to netlist. For doing synthesis, one major input for doing synthesis is your RTL. The second one input that I told you is the technology library. And I hope as a concept that I explained on technology library related to that PDK, standard cell library, macros, IO cells, all those things are clear. I hope everything in that context is clear. Any doubts in that? Okay, so we'll proceed then. Okay, so I will show you one Verilog code for a up-down counter, which I have synthesized it and kept it ready for you. That yeah, I will show you the synthesized netlist, and I will show you what does that Verilog code got translated to. 1 minute, I'll just be back. Yeah. Okay, I'm just sharing the screen. You are able to see my terminal?
Yes.
Yes, sir.
Yes, sir.
Okay. Okay. So this is an up-down counter. I hope everyone knows what is an up-down counter from the digital basics. Maybe for the one who doesn't know, I'll repeat it. For an up-down counter is a is a counter that can count from 1 to that starts from 1, 2, 3, 4, 5, and goes to a maximum number of I mean maximum number which we are defining, say 15. And down counter is something that starts from 15 and comes back to 1. So this is so this counter will count based upon is it if it is going to be an up mode or a down mode. So if you see here, this up down counter has clock, reset, up or down, and count. These are the uh, top level pins that is available. I wanted you guys to think about that chip that I have drawn, the diagram that I have drawn. With that you have to relate and see. Okay. So the in this, if you see, clock, reset, and up or down pins are the input pins, and the output is going to be a 4-bit count count pin. So and the output, you will have 4 output pin that will come out, which is count of 0, count of 1, count of 2, and count of 3. And we are declaring a register here for each value to be getting stored whenever the counting is happening. So always at the rate of passage of clock or passage of reset, begin. So if reset is equal to 1, we are initializing the counter value to be 0. And if reset is equal to 0, then we are going inside this. So here we are checking if my up or down value is 1. So here this up or down value, if I am sending as 1 as input to this value, then the up mode gets selected. And when if this is up mode is getting selected, we are also checking if count equal to 15. That means the count value has reached the maximum. So if it is 15, then we will not be able to use the up mode. So what we will have to do is we will have to reset back to 0. That we are doing. If count is not 15, then what we are going to do is we are going to increment the count plus 1 every time. Else, if count is equal to else is for this. If up or down is equal to 0, then we are coming here. Else, if count equal to 0, we are checking whether since it is a down mode selected, then we will have to check whether the count value is equal to 0. If it is equal to 0, then we are initializing with count equal to 15. We are assigning 15 to that count variable. If count equal to if that is not the case, if count equal to 1, then we are going to increment it. We are going to decrement it. Count is count minus 1, decrement counter. And this end is for this begin, and this end module is for this module. Everyone clear on this?
Yes, sir.
Yeah.
Okay, great. So I haven't written any test bench and all this. I did it for you guys yesterday only after the class. So if you are going to write a test bench, then I hope everyone will be able to do that. Is that you guys will be able to do it to write a test bench for this?
Yes, sir.
Yes, sir.
Sir,
Okay.
Yes,
can I
sir.
ask one question, sir? This, when the reset also is done by the clock only, sir. I'm just recollecting actually. Posage of reset you are mentioning, right?
So if so here
The
in
positive
the
edge of up of the clock, that is right.
yeah,
First,
positive edge, that is the passage of the clock or
yeah,
passage of the reset. Passage of the reset means 1.
one. Okay, okay, okay. I mean that is also simulated by a clock only, right? Reset also.
Nothing is simulated by clock, sir. Clock is independent, reset is independent.
Reset is independent. Okay, okay, got it.
Yeah. Okay. Uh, okay, let me come back to this. Okay, I hope if you're going to write a test bench, then you have to create a module for test bench, and you got to instantiate this EUD counter and give a instance name and provide pass values to this clock reset up or down, and then you will have to observe the value of the count in your test bench. I hope this whatever I said now is clear. Okay. So yeah. Now let's I'll show you after. So once we have taken this RTL, once we have taken this up down counter, I have done synthesis and kept it. Just to save some time, I have done synthesis before the class itself, and I have generated the netlist. I'll show you how does the netlist look like. So this is the netlist that for the RTL that you have seen, right? Uh, uh, for that, this is the corresponding netlist. Maybe what I'll do is if GVM is working, GVM is not working. Gedit, yeah. Oh, yeah. Okay. It's not working. 1 minute. Okay. So we'll go to this. So this is the netlist that you're seeing. So as I showed you yesterday itself, I explained what is this. This says at what time I have used this synopsis design compiler, date, everything. Okay, so this one, whatever you have written the counter code that I showed you, up down counter, module UD counter. Here also, this is a structural way. The netlist is a structural way of implementation of your RTL that you have written, but in a gate level netlist component will be there inside this. So there is clock, reset, up or down, and count. These are inputs, and this is the output as you as as you have said in your RTL. Uh, and there are few wires which the tool has created. And if you see, this is a how many bit counter is this?
4-bit.
4-bit counter. Yeah. So 4-bit means you will have 4 flip-flops. That is, each flip-flop will carry 1 bit. So these are the 4 flip-flops that got created. That is being picked up by the tool. This synthesis is done using SEL 180 nanometer PDK. In that, these flip-flops are available. It has picked those flip-flops, and these are the instance name for the flip-flop. See, if you see, these are all the flip-flops are same, but the instance name will be different. That means I'm going to use this flip-flop with the instance name of this, and I have instantiated and connected my pins of this flip-flop that is there in the library. This flip-flops pins are D, CP, CDN is the reset, and Q. Q is the output. So these pins are getting connected through the wires here, and these are the other combinational cells that are required for the logic. I hope everybody has understood this. Okay, for the one to give you more understanding, give you a deeper insight, I will show you how does this looks like in a schematic. As the tool, when the synthesis tool does the synthesis and finally finishes it off, it will show it will show we can also look into a GUI form also. So this is the in terminal you see this, but in GUI I'll show you that also. You're able to see?
Yes, sir.
Yes, sir.
1 minute. Yeah. So this is the up down counter. And if you see this now, this is going to be a chip for you. Now, whatever you see here, these are the inputs and this is the output, which is 4 represent 4-bit. Okay. And the input is clock, reset, and up or down. Now, if I double click on this, you will be able to see the logic that is there inside this. You're able to see?
Yes, sir.
Yes, sir.
Yeah, 1 minute.
Sir, which tool was this?
So this is Synopsys Design Compiler. So you're able to see? So what all these things are like? Let me zoom a little bit. Okay. See, there are so this is a D flip-flop. The rectangle ones are the D flip-flops. If you see in this image, you will find how many D flip-flops should be there?
4.
Yeah. Guys, please pay attention. Others also please answer. I don't want to be like yesterday. I will ask someone to unmute and answer also. So please pay attention. These are very fundamental things. If you don't understand this, the entire course is going to be a useless course for you. So please pay attention. I'll not come back to this in any of the other classes, in any of the upcoming classes. So here, so you, as you said, like you will need 4 registers. So the one register is here, second one is here, third one is here, and the fourth one is here. So let's a little bit zoom in and see. See this flip flop, this D flip flop is taken from the technology library. I wanted you guys to remember the name of the flip flop. It is DFs. It is going to be what? DFC RQ1. So that's what it's showing here. Okay, 1 minute. Yeah, you are able to see a small. There is a lag. Ramya, can you mute your mic?
Yes, sir.
Yeah, so this is one register. So the name of the register is going to be and this is the name of the flip-flop. Yeah, flip-flop is DFC DFC RQ1 that we have seen in the netlist. Okay, and the instance name is count underscore reg underscore 0. Same D flip-flop only is being called here. Same D flip-flop as in DFC RQ1 is called here with a different instant name count underscore reg underscore 1. So this is how a netlist look like. Okay. Any doubts? And if you see, these are the pins, clock, reset, and up down pins are here. And the output is here. Yeah, tell me,
Good morning.
Marufa. Yeah. Marufa, your voice is very feeble. I think there is an issue with your mic initially itself. Like, can you check that or you can text it? Yeah, and someone else was asking.
Good morning, sir. This is Vineet here.
Yeah, Vineet.
So, sir, we'll be using the same flip flop throughout for the other four flip flops also, sir.
Yeah, the tool has chosen this four flip-flop with the, I mean, I mean, there are multiple variants of flip-flops are available. Okay. This flip-flop is the required for this design. That's how the tool has chosen. And that
No,
is
sir. What
optimal. Yeah, tell me.
what I'm trying to ask is now this particular flip flop DS1 is there, no, sir.
Okay.
Will that same flip flop be used as register 2, register 3, and register 1?
No, no, same as in same register, same flip-flop, but in a, I mean, you will have a separate flip-flop for that. It is not like same. That's why you see here, this is a separate flip-flop. This is a separate flip-flop. This is a separate flip-flop. And this is a separate flip-flop. But you are using same same model that is being picked up from the library. There is one flip-flop available from the library, but what you are doing is you are taking that flip-flop and giving connections in this format. I mean, the tool is connecting it in for this particular, for the for this inverter to get connected here. The output is going to a XOR gate, and it is picking another flip-flop of the same as in that also has a D input, Q output, clock input, and reset input, and it is using it for implementing here. It is instance. So I hope you should be clear about what is instances.
Yes, sir.
Okay. Vineet, your background, you're from which college? I mean, which year?
I've just finished my BTech last year. I just graduated last year.
Electronics?
Yes, sir.
Okay. So you should know like what is instance, you know, right?
Yes, sir. I just
Okay.
have a vague idea of it. I
Okay, fine. So you are instantiating the same flip-flop four times, but using it for your functionality to be used. That's all. But you'll have independent four flip-flops.
Okay, okay, sir.
That is why you have different instance names. I showed you, right? There are instance names that those are different. Only the flip-flop that you are using is of the name same thing that is picked up from the standard cell. But if you see here, this is count underscore reg underscore 0, here count underscore reg underscore 1.
Yes, sir.
Okay.
Thank you, sir.
Yeah. Yeah, Marufa, you are done. Any, I mean, did you send your doubt? Uh, Marufa, yeah, if you want, you can talk. Let's see if it is.
So I think there is issue in my
No, I am not getting in. Does anyone else understand what Marufa is saying?
Her voice is not clear.
Yeah. Fine, let's move on. So I hope this gives you a clarity on what is happening in synthesis. What is actually happening in synthesis? I hope this demonstration of this gives you. Yeah.
Sir, this layout visibility is this is really good actually to visualize, right? How they are connected with different. So it is generated by the compiler, right, as part of the synthesis, correct? This entire layout.
Yeah. Yeah. This is being generated by the synthesis tool only. It is giving you
Yeah.
this kind. So generally we don't use this GUI. We always go with the terminal. Through terminal only we do the synthesis and see in terminal only we look into the log and find out if there's any issue. This GUI
Okay.
I'm showing it for people who are like freshers. Will get a understanding, like you got one understanding at your insight. No, that insight or
Correct.
giving that
Yeah.
insight I have shown the.
Okay. Okay. Okay.
Okay, so let me close this.
So, what are the activities we have to perform in the synthesis level? Now, like from this netlist, we move to synthesized. Any command we have to run or what to do?
Yeah, that and all I'll tell you when you are in coming to the hands-on, right? That time I'll be able to tell you those things. I'm just giving you an understanding now here, like how what will happen, what does that synthesis do?
Okay.
Okay. So I hope you are clear. So whatever you have seen in the diagram is part of this netlist only. This is the netlist, and that only you have seen in the diagram also, the schematic. So this is the netlist that you got. Okay. Now, while yesterday when I was telling you about doing synthesis, the first input for doing synthesis is your RTL, which I showed you couple like few minutes before, the up down counter RTL. Second one is the technology library. Yes, the technology library, it is we are currently for this particular example, we have chosen the SEL 180 nanometer technology library. From you taking that library into consideration only, it has done this synthesis and given us this netlist. Okay, so what do you want to see now?
For constraint.
Constraints, that is another input for synthesis that is pending. But whatever I told you now, there is one thing that you will have to see. What is that? I see, I repeat it. I want someone to answer. I repeat again. So for doing synthesis, the first is the RTL input. For doing synthesis in RTL, I have shown you for doing synthesis, up down counter RTL I have shown you. Then using the technology library, the in
Time,
what? Yeah, Ramya.
timing constraints.
Yeah, timing constraints, we'll come to that. But other than that, there is one thing that you will have to see. Yeah, I mean, I have to show you something. I wanted to get it from your side. What is that?
For
So,
technology library.
Output.
exactly. Jiban Roy, you're right. It is the technology library that I haven't shown you, right? You're using the technology library and doing synthesis and got your netlist also. I said you these are the flip-flops, these are the gate standard cells that is picked. So from technology library only it I would have picked, no?
Yes,
So
sir.
yesterday's class I said like I will show you the technology library. You got it? What I'm saying?
Yes, sir.
Okay. So okay. So let me show you. See, this is the PDK given by the SEL, Semiconductor Laboratories Fab, Chandigarh. This is how it looks. So it has a lot of files inside this. So in that we are going to go only right now focus on the standard cell library. Okay. We will explore other aspects of this PDK through while we go into this course more detail. Guys, please don't confuse what I mean, you who are seeing lot of files, But don't get confused. Now your focus should be what is there in the standard cell library that is given. So here, this is the in technology library, we have taken the standard cell library alone, which has components of combinational cells and sequential cells, that alone. We have not seen the macros. We have not seen the IO cells because our design doesn't have any macros. So we have not seen that. So we are will open up. So I said no, in the standard cell library will be in two different format. One will be a .lib, another will be a .db. So .lib I'm opening. Yeah, someone want to say?
Oh, I just wanted to ask if the contents of both those files are same, just the formatting is different.
Yeah, formatting is different. So if see, I have opened the .lib, okay, but if you try to open the .db, it looks something like this. It is a not readable form. This is an encrypted form, but both the contents will be same. It is just for the tool. If you're going to take Synopsys design compiler for doing synthesis, then you will be using the .db format. If you're going to use Cadence GenS for synthesis, then you will be using the .lib format. It is the tool compatibility. Okay, so if you see inside this library, what does this have? It says about what is the technology this all cells are being uh, manufactured through, what technology. It is a CMOS technology. That's what they are saying. I will not be able to explain you everything that is there in the standards this .lib, but I will try to explain a few things which are very important for this course. So if you see here, it says the time unit is 1 nanosecond. That means whatever cells that is there inside this standard cell library, technology library, whatever time aspect is being taken care for each cell, those are having a unit as 1 nanosecond, and as well voltage as 1 volt, current as 1 microamperes, capacitance as 1 picofarad, resistance as in kilo ohms, leakage power unit are in picowatt. Leave all these things. So this is the library name. Whatever is being told here, this is the library name. So can someone tell me what was the flip-flop name that was there in the netlist? We can search for that flip-flop. And if you see what is the size of the library .lib, if you want to see how many lines are there. So these many lines are there in the .lib. You're able to see the line numbers, right, on the left?
Yes.
So DFC RQ1.
DFCRQ1, yeah.
Yeah, so let's search for DFC
Control F will work here.
RQ1.
Yes. RQ, yeah, correct.
So here it is telling about this cell. DFC RQ1, it is telling this is the cell name, DFC RQ1, and it's saying the area, that is the size of this cell. How big is this cell? It is 65.86 micrometer square. Then it is telling you about cell leakage power. So how much is the leakage power that the cell will have? It is going to be 873.1 picowatt. And so what are the pins, input pins for this? I mean, we are going to see what are the pins available for this D flip-flop. So you see pin CDN, and if you come down, you see pin CP. The CP is the clock pin, CDN is the reset pin, and pin D is the input pin, and pin Q is the output pin. Okay. So we will see what is there inside this. So what they're telling here is for pin CDN, there is a pin capacitance that always comes with pins. So defaultly they are saying like the capacitance for the CDN pin is this much picofarad. So how are they extracting these values? How are they extracting? How are they, as in the fab people, how are they extracting these values for the CDN pin to be this? And the fall capacitance is this. The minimum pulse width flow is this. Rise capacitance is. So they are giving some values, right? That's what I was telling you yesterday. There is something called as library characterization that they do, the fab people. So the first step that they do for designing this D flip-flop is they start drawing the layout. Like I have shown you for a CMOS inverter. They start drawing the layout for D flip-flop. They maintain the height of the flip-flop. They keep it as same as the other standard cells available in the technology. They only vary the width of this and try to implement the D flip-flop logic. So once they have completed the layout, there is a process where you can extract the capacitance for this pin, whatever is the pin that you have drawn for this flip-flop in the layout. They will extract information. So that's called characterization, and these are the output generated. These are the output information that is getting generated for the particular flip-flop that you have designed. There are tools available that will help you to give these informations. So what will with this information, what are we going to use is like whenever you are doing synthesis, these informations are required for for going and picking up only this particular flip-flop. So if you see, there is not only this flip-flop that is available in this PDK. If you see, there is DFC RQ4. You're able to see here DFC RQ4. We have seen DFC RQ1 previously. Let me search like this. Cell DFC. Huh. See, you're seeing cell DFC RB1. Then you have DFC RQ2, DFC FB4, DFC RN2. So what I'm trying to tell you is here you will have multiple flavors of D flip-flop. One flip-flop will be having a lesser drive strength. One flip-flop will have more drive strength. One flip-flop will be good at meeting the required timing. One flip-flop will be good at its area. See, for example, this area of this flip-flop is going to be 68.99 micrometer square. Okay, RN2. But if you see FQ4, the area is 75.26. This is bigger than that. And this is another flip-flop which is smaller than that. So whatever is your requirement as per your design, if you are going to look for performance, you want only the I want to get a high frequency of my design. I wanted my design to concentrate and work for higher frequency. Then you don't care about area and power. So it will choose the one which is having good performance. So how does it performance and all is getting? How does the timing aspect is chosen? Is, for example, in this flip flop, you see the timing here. And from this value, it picks up. These are the restricted values that is available for the CPN pin timing. And similarly, that you will have timing information for this D pin, like how after how much time the data will enter into the D pin. Similarly, for Q pin. So how much time? So this is like a matrix table. From this table, it will pick it up like according to the constraints that you provide, timing constraints that you provide, according to the power constraints you provide, according to the area constraints you provide. the synthesis tool will go read this library, pick the necessary flip-flop, pick the necessary standard cell, and then give you an optimized netlist. What does an optimized netlist mean is, according to your requirement, if your requirement is going here, this is a 4-bit counter. So there will be 4 flip-flops, okay, and each flip-flop is going to get controlled through this clock as a reference signal only, because at every passage of the clock, the Q will read whatever is there in the D value. The Q will give the output. So my reference signal is going to be my clock now. So let me see, like, if I'm shrinking the clock, okay, let me see this. I have consider this clock time period as 10 nanosecond, and for this 10 nanosecond, um uh what is the corresponding frequency for 10 nanosecond? What is the relation you have between time and frequencies? T is equal to 1 by f, or f equal to 1 by t. That is the relation. I mean, Jibendra, you know this?
Yes, sir.
Yeah. So if I want to see what is the frequency for this 10 nanosecond, which is going to be 1 by 10 nanosecond, this comes to be 100 megahertz. Now, this time period is 100 megahertz. Now, let me try to shrink it to whatever I have drawn my time period as 1 nanosecond now. From 10 nanosecond, I'm shrinking to 1 nanosecond. So for 1 nanosecond, then it will become as 1 by 1 nanosecond, which is going to be 1000 megahertz, which is 1 gigahertz. So so what is happening? My flip flop is taking data and giving out data. For this case, it is giving at 100 megahertz. It is taking input and giving output. If you consider the waveform to be this, then if you consider the clock to be 1 nanosecond, then at 1 gigahertz, my input is taken, and output is given out. So that is the importance of clock. So if that means what? If you are running at 1 gigahertz, you are able to do better performance, right? You will be able to take many inputs, and if you're going to take 100 megahertz, then you're only going to use it for some time. See, if you are saying here itself, if you see in this particular one cycle itself, if you're going to use it multiple, like 4 cycles like this, that means what? The time period is less and the frequency is going to be more. So someone wants to ask something.
Yes, sir. Sir,
Yes,
how will check this PPA part, power performance area like heating, scaling, leakage, those things? How will see this one?
we'll come
This
to that. That's a different topic. We'll come to that. Anyone else? Okay. Yeah, Lakshmikant, you want to ask something?
No, like I got it, sir. I got it.
Okay. Fine.
Sir, I just have a doubt, sir.
Yeah, Vineet.
The clock we're giving now is in nanosecond, right, sir?
It can
Can't
be
we?
nanosecond, it can be in picosecond also.
So if we give it as a picosecond, the frequency will also be less, sir.
Yes. Frequency will be more.
How?
Nanosecond compared to nanosecond, picosecond is still smaller, right?
10 to the 12, na? Minus 12. This is nano 10 to the minus 9.
So compared to nanosecond, picosecond is comparatively, it's still lesser, right?
Yes, sir. Compared to nano, pico is still lesser.
So when time period is less, then the frequency will be more.
Okay. Yeah, sorry, sir. I just forgot the
No
basics.
issues, no issues. This happened to me also, Vinay. When I was studying, these all things happened to me also. I'm seeing part of me in only when you guys are asking doubts. I see myself only. So no issues.
Okay, sir. Thank you, sir.
Yeah. So yeah, coming back. So what I'm trying to say you is this clock signal plays a very vital role, and we wanted to know. So if I'm using this design for 1 gigahertz, that means what? My design will work for 1 gigahertz. My design will work for, that means what, 1000 megahertz is 1 gigahertz. That means my design will work for 900 megahertz. My design will work for 500 megahertz. My design will work for 50 megahertz. My design will work for 100 kilohertz. My design will work for 10 kilohertz. My design will work for 1 hertz. So I am saying if my design is able to run for 1 gigahertz, it will be able to run to the lowest as much as possible it can. But this doesn't say that my design will, if my design is running for 1 gigahertz, it will not give an assurance that my design will work for 1.1 gigahertz. That will not happen. So what is that determines this? That my maximum frequency is 1 gigahertz. What determines that? That is being handled by the synthesis tool by considering the timing constraints that you give. With that, the tool will consider and take your RTL, take the library components. The library components, each cell will have timing information, and from those timing information, the synthesis tool will pick up whatever necessary cells that is required for meeting the timing require constraints. And if it is not able to meet the timing constraints that you have given by, and it is not able to find the equivalent cells that in the library for meeting the timing, then that is the threshold. That is what will tell you that my design is the maximum frequency is 1 gigahertz. It can't work more than that. There comes the term called slack. That if my slack is negative, that means my design is, that is the worst frequency that my design will not work. So your slack should be always positive. We'll come to that. I mean, just I'm giving you this term, but I need not take it now. We'll come to that. Any doubts until now? It's clear. So I repeat this concept once again. So you are going to give the timing constraints in as one of the input to synthesis. In timing constraints, you will tell the time period of this clock, how much time period it is going to be. Okay.
Sir,
And
sir, sorry for interrupting. Sir, can you show like how exactly the timing constraints will be there?
yeah, Lakshmikant, I'm going to show you. But
Yeah.
yeah, I wanted to make sure that give you an impression like, are you confident of my understanding? Is it reached to you, everyone? So I'm just repeating it and I will show you the constraints file to you. How does it?
So, sir, if the slack is negative, we will have to adjust this timing constraint, right,
Exactly,
accordingly.
exactly. Yeah, I'll show you the
So,
timing constraints.
so
Then we
yes,
will,
so that
yeah,
shows that it will not be able to handle that level of timing.
exactly. Yeah, I'll come to that. Let's
Okay, sir.
slowly
Yeah.
come to that. I understand that you guys are really understanding what I'm saying. I'm happy for that.
Okay, sir. Okay, sir.
Yeah. Yeah. So your synthesis. So please listen what I'm saying now, because that is more important. So your synthesis tool will take RTL, your RTL, and then it will take your RTL. Sorry, 1 minute. Yeah. Your synthesis tool will take your RTL, then it will take your dot lib. In the dot lib, as I've shown you, each cell will have its own timing information, its own power information, its own area information. Okay. So when the synthesis tool picks up one particular cell, say a flip-flop or an inverter or anything, how will that go and choose that particular cell is determined by the timing constraints that you give. If your timing constraints you are mentioning says like some as 10 nanosecond, and to meet that 10 nanosecond for your entire design, that RTL that you have written, The tool will help. It will try to achieve that. Will try to run synthesis and do an optimal synthesis, and then if it is able to meet the required timing constraints, then it will generate a netlist with a slack as positive. Suppose it's not able to meet the timing, then your slack comes to be negative, and that negative means negative of a value, say minus zero point 0.5 nanosecond. That means if you're given timing constraint and the constraints are 10 nanosecond, that means you will require 10.5 nanosecond for your design to meet the timing. Got it?
Sir, what are the conditions that make if a design doesn't match our timing constraints, and how can we consider it, sir?
Yeah. So that depends on how do you write the RTL, how do you write your Verilog code.
Yes, sir.
Yeah, we will come to that. That is going to be the next part of the class, like on the next week, static timing analysis, that will come, STA, where we will say like what are the components that determines my slack in the design as in the RTL. Okay.
Okay.
Suppose your design requirement is you will have to close your design at 1 gigahertz, but you are only meeting your design at 900 megahertz. What should I do in my design so that I meet 1 gigahertz? Correct? That has to be that, and all I'll tell you in the upcoming classes. Now, now is this clear? Shall we go and look into the constraint file?
Sir,
Yes,
what
sir.
is the STA full form, sir? STA full form?
Static timing analysis.
Static timing analysis. Okay.
Shall we go ahead?
Yes,
Okay.
sir.
Yes, sir.
Yeah.
Sir, which compiler you are using for this one? This custom compiler or fusion compiler?
Design
Synopsis.
compiler for Synopsys design compiler for
Design
synthesis.
compiler.
Yeah. Custom compiler is not for synthesis. Design compiler is for synthesis.
One is also fusion compiler.
Yeah,
That is
Fusion compiler is there, but that is synthesis plus PNR for Fusion compiler. Okay, let's see the up down counter.sdc. So this SDC extension is this is the constraint file that we give input for doing synthesis. Okay, SDC is called Standard Design Constraints or Synopsys Design Constraints. SDC is a file extension for constraints. Okay, it's called Standard Design Constraints or Synopsys Design Constraints is the extension's full form. So if you see, I have just kept a very minimal constraints here. You can add lot of things in this constraints, but I have just for the sake of simplicity and for you guys to not get confused, I have I have said like what is there very minimally. Okay. So if you see, coming back before that, let's have a look into the RTL that we have. So I wanted to see guys and remember what are the inputs and outputs. So you have clock, reset, up or down, and count. So what is the name of the clock signal here?
CLK.
CLK.
CLK. Yeah, capital C and small lk. Correct. Now, what we are going to use it in the constraints is we are going to use that CLK pin that is there in the design. So we are telling the tool, synthesis tool here, that you create a clock. That is, this is a command for the synthesis tool with a period of 2 nanosecond. Nanosecond is a default thing that is said in the .lib. I hope everybody remembers. When I open the .lib technology library, it says like in this entire library, in the entire .lib, all the units are in nanosecond for timing. All the units of power are in microwatt. All the voltages are in millivolt. So from the standard cell, uh, uh, the timing unit will be considered. So you have to just mention the number. So it is going to be 2 nanosecond. And hyphen waveform. This is like how does that time period looks like? What is a duty cycle? Duty cycle is the first half and the second half of the time period, right? So it should be equally there. So 0.0 to 1.0, which is like 50% duty cycle of the waveform. Okay, sometimes the duty cycle also, as per the design requirement, they will change. Like you have 20/40, 20/80, or 60/40, like that. So this is like 50/50, the waveform of the of the period of the clock. Then get ports is a command that goes and picks up from your RTL, that counter, up down counter RTL. It goes and picks up the clock signal which is of this name CLK. It we are mentioning here so that the tool will go and pick this particular pin and identify and assign this as a clock. So that's what you are creating as a clock. Any doubt in this understanding of this first line?
So
Okay.
while defining this clock, so multiple people will be using. So it will be based on this user. It will take. There will be multiple clocks will be designed. Then it should be unique, right?
Yeah.
Yes. Yes.
Okay. So next you have set input delay and output delay. You can leave these things. We will cover in the upcoming classes. So as of now, you just remember there is some input delay and output delay that you are specifying. This is the one that you are going to tell the tool that you please run my design for 2 nanosecond. Okay. Okay. So using this two information only, that is passed to the synthesizing tool, that this timing constraint, and it passes, and yeah, that's all. Then it will tell you whether my design is met or not, which we will cover it in the next class. Coming Saturday's class, we'll see what is the timing aspects, which, because if I start, it will take another half an hour to understand and complete that. So maybe I'll show you where is that. So if you look into the reports, please don't ask me now because this needs an explanation. I'm just telling you, I wanted to show you, that's all. Where does the Slack come into picture? So here only you have created the clock time period is set, and this says, it says that Slack is met, which is like saying 0, the Slack is met for 2 nanosecond. That means this counter is going to work for 2 nanosecond is how much? 2 gigahertz, correct?
Yes, sir.
Okay. I'll explain
Mostly it's
all these
2
things,
gives you
that
500
is,
megahertz, right?
sorry, 500 megahertz, correct. 2 nanosecond, 20 nanosecond is 500 megahertz, right? Sorry, wait, I'm also getting confused. 1 minute. Yeah, it's 500 megahertz. I'm sorry.
Yeah, 500.5
Yeah.
gigahertz.
Yeah, fine. I think that's all I wanted to say. Any doubts until now? We will come into this, like how did it I mean this mm, how does the tool determines the slack, all those things we'll explain that in the next class. But before that, I hope everybody is clear until now. Any doubts? Ridvik, you got something. Sir, since the processor has multiple clock domains for different hardware blocks, on what basis do we declare the processor frequency? So in constraints, I said no. I have given you a very simple constraints. That's what I said, Prudvik. It's a very simple constraints that I have given you. But for a processor and all, if you are writing a constraints, you will have to include all the clocks that is there in the processor, and you have to specify which clock, what frequency you are expecting. in the design. All these things you have to tell it in the constraints, and then you will give, and the RTL, the processor Verilog code, you will give as an input, and then the synthesis has been done. Is that okay? Please unmute and say.
Yes, sir, it's fine.
Fine. Any
Sir,
doubt?
is writing this SDC file a manual work, or is do we just provide some constraint to a tool or something?
It's a manual work. You will have to write this and provide it to the tool.
So if we are doing a processor, then we'll have to write constraints for all the clock domains, and then that input output related stuff, right?
Yeah,
So
yeah,
we'll
that's
have to
a
manually write for each and every one of it.
yeah, we have to write because that's the job of the designer. Whenever the designer is writing a code for processor, he will be aware like which clock, what are the clocks that is there. So he'll be able to give you the constraints.
Okay, okay. Also, when we're going back to the synthesis part, so suppose we are using a low power design, we are incorporating clock gating. So does that should some file related to that be added to the synthesis tool, or
If you
does it come
are
in later session?
if you are going to do clock gating as part of your RTL, then you need not include anything. But if you are asking the synthesis tool to do clock gating and all, then will have to mention it in your synthesis script itself that please do clock gating on these kind of these modules and all. Then you have to tell the tool.
Okay, so this is a separate file that we have to add in that case. For example, you write the low power system in UPF format. Let's say
Yeah.
so when you write that, then you have to apply it as an input file to the let's say the synthesis tool as well.
Yeah. So right now you are giving a separate file for timing constraints, right?
Yeah.
Similarly, when you're saying about low power, everything that is a power constraints. So you will have to give a unified power format, that is UPF file. If you have, you will have to separately define the constraints, tell like which module wants to work for which voltage domain, everything that you will have to define, and then you will have to give that as a separate input.
Okay.
Guys, any doubt? We'll spend some more 2 more minutes here itself, and we'll clarify the doubts. Then we will wind it off. And please don't forget, uh, until now, whatever I have taught, please don't forget, because on the next class, when I start, it should not be like you are very much fresh. Please carry this energy, and because whatever I'm going to tell you in the next class is more related to whatever I have said you now. So you should not forget anything.
Sir, I have a doubt, sir.
Yeah, Jayavalia.
Sir, does the SDC define elements like PLL in the actual hardware, sir?
No, SDC will not tell you anything about the hardware. Hardware part is always told in your RTL.
Like I mean, clocking elements, like phase lock loops and so on.
Yeah, PLL is the hardware, right? Which generates the clock.
Yes, sir. Like, is it defined in the RTL itself, sir?
Yeah, it has to be defined in the RTL itself.
Okay, sir. Got it, sir.
Yeah. Yes, Satya, sir.
Sir, nothing, sir. I might need to drop off if that is okay, sir.
Fine, fine. Let's all drop off. If
Yeah.
anybody has any doubts,
Yeah.
I think
Thanks a lot for the class, sir. Thank you very much. Yeah.
yeah. Thank you, Dinesh. Somebody is asking some doubt. Others can drop off if you're fine. I'll just.
Thank you, sir.
Yeah. Demonth, sir, which Linux software we have to download? Any Linux is fine, Demonth. Ubuntu is ideal. Anirudh, tool access and all, by end of the class you will be given. The access will be given. That physics wala will reach you on that.
So one final doubt.
Yeah, Rohit.
Suppose if we before writing RT, will actually plan a circuit, right? This is the type of circuit we want, and then we write a logic according to that, right?
Yeah.
Suppose let's say like one portion of the circuit that we are trying to do in a different way, and we draw our own layout for it, like hypothetically. Then once we do that, can we then incorporate this back into the digital logic workflow?
Yeah, that you can do. See, somebody was asking about PLL, no?
Yeah.
Phase lock loop. That phase
Yeah.
lock loop is separately a different design by itself. So that
Okay.
you are going to, if you are going to bring into your design, you have to instantiate it. That's all.
Like the reason I'm asking is, for example, the place where I work, there's a project student whose work is to draw a layout while giving consideration to what's this, single event latcher protection.
Okay.
So for that, she needs to create additional layout to prevent this this, what do you say, to give some radiation hardened effect to the circuit.
Okay.
So this is hypothetical because this won't usually cross with the normal ground card circuitry. But if we draw this separately with regard to all this radiation hardened or tolerant layout, can we
Okay.
then incorporate this part back into the, what do you say, the PDK of the regular, what do you say, synthesis?
No, you can't do that.
You have to do it separately.
Yeah. If you are doing red hat cells, if you are doing into some red hat designs and all, that has to be handled separately.
Okay. And because when we draw it on our own, then it might not match with the like height and
Exactly. So that's why this has been given by the fab. That's why you should not modify your fab cells and all. Yeah, if you
okay.
are
So
designing,
it will be, we should create it like a separate module and then it's connected externally.
yeah. So so the PDK is provided by the fab, and it is you're allowed to use only that. You should not introduce any new designs, and then you incorporate inside that. That should not happen.
Okay.
Yeah. Some Tejas sir, I have a query beyond this course. Yeah, you can unmute and say. Others can drop if needed.
Sir,
Yeah, Tejas.
sir, my English knowledge is not at all.
I think physics wala team, you can stop the recording. I mean, Tejas was asking something. Everyone, good evening.
Good evening, sir.
Hello, sir. Good evening.
Good evening, sir.
Good evening,
Good
sir.
evening, sir.
Did you guys able to finish that exam? The exam that was given, is it done?
It will be given today at 8 o'clock.
Yeah, it's this evening, 8 p.m.
This evening, sir.
Okay, right. Good evening, Marufa. Okay, so we'll get started. Okay, so to summarize the last class, can anyone tell me what was taught on the last class in a very 1 minute brief?
Time constraints, sir.
Yeah, timing constraints. Yeah, we have started with that, and I mean we have ended up with that. But overall brief, what I was told on the last class. Anirudh.
Sir?
Yeah, you were there in the last class.
Yeah, I was not there, but I saw the recording, sir.
Okay, can you give a brief of your understanding of the last class?
Sir, first we saw about the synthesis, the RTL, and we saw the technology file, and you saw an example of the technology file, and some timing values was there regarding the slack, and uh, and we also in the end we saw about the clock set input delay like that.
Okay, so that was the later part was timing constraints.
Yes.
Okay, Fine. So, okay, let me start. So I hope my screen is visible.
Yes, sir.
Okay. So this is what we were seeing in the last class. I will quickly summarize whatever we have seen. So the first stuff is the writing the RTL, and after once your RTL is done, the RTL is taken to synthesis. In synthesis, the RTL is converted to gate level netlist. Your RTL may be in Verilog, vshell, system Verilog, spec system Verilog. At last, everything gets converted to a gate level netlist, which is nothing but a structured Verilog netlist. This has been this synthesis process is done using using EDA tools, Synopsys, Cadence. Fine. So what are the inputs for synthesis? One is the RTL and another is the technology library. Once these once this two is, please kindly mute. Okay. So once the RTL technology library is given to synthesis tool, it starts the process of optimizing the design and will give you an optimized netlist for your required timing constraints that you are giving here. So RTL, technology library, and timing constraints are the three inputs that you give for the synthesis tool to get the netlist. And I was telling you about how do you basically here meet the timing. If your timing is, if you want to meet your design to 1 gigahertz, what that 1 gigahertz actually means is, that's what we were saying. And I was showing the timing constraints file. How does that look like? Okay. Today, what we will see about the uh, synthesis, what all other aspects of synthesis is that has to be seen. First is what after synthesis, why once you do the synthesis, what is it, how is it going to be relevant for you thereafter? So once your synthesis is done, your RTL, and then what?
Technology library.
Yeah, technology library, that is .lib. So
Time
yeah,
constraints.
Timing constraints.
yeah, timing constraints. So this .lib can also be called as timing library. That's because if you remember when I was showing you the .lib, it was giving a, I mean, it was having lot of timing values, right? For every pin, for whatever logic is, whatever the delay that is accounted inside that cell, everything is accounted in that. So we can say this technology library as timing library also. So once this synthesis is done, you will get the netlist, netlist.v. Other than this, what output you get synthesis is one is certain reports. These are some very important reports that you get to analyze about your design after synthesis. First, in reports, you have timing reports, area reports, there are other steps right after synthesis for to take to further move forward whether your design is ready. So all these things will be considered in that. So with these reports, what you can estimate with this all these reports, what you can estimate is you can estimate the size of the chip. You can estimate the size of the chip. You can estimate the frequency of the chip that is going to be finally taped out, and you can estimate the maximum power that it can draw. These could be estimated. We will see how we will see. Maybe tomorrow I'll show you all these reports that that is generated for the design that we were last time using, that counter design that we were using, up down
So
counter.
size and frequency are two factors which we are providing, right?
Size and frequency
Are two factors which we are providing.
we are providing. I'm saying the reports that comes out right after doing synthesis will tell you that frequency means what, the time period that you are giving in the timing constraints, correct?
Yes.
So that translates to frequency. One, if your design is able to meet the required timing, that means it is able to achieve certain frequency, and that is the frequency of my chip.
So it may happen that chip may not attain means reach our target. It can happen.
Come again?
So it can happen, right? That the chip we are building will not reach the target frequency which we want.
Target frequency is the time period you specify in the timing constraints, correct?
So same will come out in report, right?
Yeah, same will come out in the report.
Okay, so why do we need to estimate it then?
Why do we need to estimate it?
Means from
Okay.
report.
No. Okay, report we are getting it. So it's I got your question. It's not about estimation here. It's about estimation of the size of the chip first. And for this size of the chip, what is the frequency that will be able to meet, that we will be able to get it from the report. Timing constraints is something is the requirement from the designer, from the specification engineer specification only. But at the report level, whether you are able to meet the timing report, that could be analyzed and confirmed using the reports. That's what I mean to say estimation there.
Okay.
Okay, so coming back, So all these things can be estimated. Now, how can this then be taken forward? We will see looking into a report. Maybe by in the by end of the today's class or tomorrow's class, we will look into the report and we'll see. Now,
One small question, sir. Like,
yeah.
If the frequency is provided as input and we are getting it as part of the reports also, and size of the chip also we are getting as part of that report, right? According to that size, the frequency will be aligned. So will there be any variation between the input one and the output one, sir? Frequency, because according to the size, it will be aligned, right? The frequency.
No, so whatever in the timing constraints you are giving, that's what I was telling to Bhavi Gupta also. Whatever you are giving in the timing constraints, the frequency, that only you will be achieving it at your report level.
Okay.
Okay, and there is one thing that here about the which we will be seeing today. One aspect of the timing library is you will have multiple corners in timing library. You will have multiple corners, and you will be only taking the library in a slow corner. Slow corner library will be given by the PDK, and you will be using that slow corner library for meeting the timing that you are specifying in the constraints. That means at synthesis level, whatever you are achieving the frequency, that is the minimum frequency that your design meets. The maximum frequency is not this what you are specifying in the timing library. Sorry, what you are specifying in the timing constraints. The maximum frequency will be a little more than that. I come to that. I know that right now you're understanding. I'll come to that. So for doing that, let's analyze something. So you have in the timing library that you give for doing synthesis, you have multiple corners. So one you have slow corner, then you have typical corner, then you have fast corner. Okay, what is this? All these things is. So can anyone tell me how in the timing library, right? The technology library, how are the values being the values that you saw while opening the .lib? How are these values being characterized? Where those values are coming from? Bhavi Gupta.
Thinking, sir.
So you remember I was opening the .lib and showing, right?
Yes, sir.
So processor, and then we will go ahead with the session. Any doubts until now?
Sir, how much time it took to generate this netlist, sir? I mean the synthesis one completely.
My machine is a very good machine. So very good, like as in very high configured machine. So it took around 15-20 minutes for this. But if you are having normal machine, it will take more than 1 hour or so.
With all those huge number of files.
Yes. Yeah.
Log files.
Yeah. So
Excellent.
So we will. I'll show you the netlist. How the netlist look like for this Shakti processor. You guys are eager to see that?
Yes, sir.
So this is the netlist that got generated. Okay. Now just see the number of lines. You remember the netlist for counter, right? There were only 4 flip-flop in the top and rest were in combinational cells in the bottom. You guys remember, right?
Yes.
Yeah. See the total number of lines here. It is like 255,456. Nearly 2,55,456 lines are there. So this is very small processor. Okay, whatever I showed you is not a complex thing. It's a very small thing. So you do not think that it's a very big design. It is not at all a big design. So let's see the reports and see how many. What do you want to see in the report?
Can you see the Slack, sir?
Yeah, Slack. We will see other. What else you want to see in report?
Area.
Area.
Size and
Power.
Size of
frequency.
this frequency.
Frequency, sir. Frequency.
But so see, the first thing as an engineer, VLSI engineer who wants to implement a design in on a chip, take forward and do right, like we'll always look for the total number of
Size.
flip-flops that is there in this design.
Yes, yes.
Okay, because the total number of flip-flops is it will tell you that the design is so much big. Right now you have seen an up-down counter with 4 flip-flop. Okay, now see how many flip-flops does this have. In that QR report, we will go directly and see the information about cell count. See the sequential cell count, how many are there? 28,948. So how do we always say this as in industry, we say what is the size of the design? We will say 28K flip-flop count. The flip-flop count will not change at any point of time. The flip-flop count will not change. Once your RTL is done, it is given to you. This 28,948 will stay 28,948 until the final final design that is going to be sent to fab, right? Until that, it will remain as 28,948 only. There is no +1, there is no -1. But if you ask me about the buffer count, inverter count, combinational cell count, these may change during implementation. So after synthesis, you go to floor plan, placement, routing, everything, right? At those places, these may increase or decrease, whatever can happen. But the sequential cell count can't increase or decrease. Should stay this same number only what you are seeing it in synthesis. Why so? Suppose it is increasing. What does that signifies? Suppose in synthesis, it's showing 28,948, and while doing floor plan placement, routing, and all, at some point it is showing like 28,949. What does that mean? What does that implies to? Just guys, this is a very interesting question. I mean, you have to think and answer. What does that mean if the flip-flop count is increasing?
Size is increasing.
Time will increase.
I'm saying this should not increase, but if it is increasing, what does that affect given what does that affect you?
It will make a delay.
No. Okay, it will make a delay. What does that
There's a
delay?
modification in design.
Exact. The RTL, the exact functionality will be changed, right?
Yeah.
The functionality of your design will change. What does that one flip-flop, if it is getting introduced, that means one place it is going to store some information, read or write some information, right? In a flip-flop. That means the actual functionality that you have written in your RTL is not going to stay that way. It is going to change. So that is why you don't have any right to increase or decrease the flip-flop after synthesis. Once your synthesis is done, if that is sequential cell counts has to be the same until last. If it is increasing, then something you have done some blunder in the implementation at any stage. It might be at floor plan, it might be at floor placement, it might be at routing, anywhere. Guys, got this point? See, these points and all in any classes, in any of the courses in say whoever is taking the physical design course in many, there are many coaching centers doing, they will not say all these things information, because whoever has worked on, who has done multiple tapers, these are industry known things which people will not be delivering it at any academic course if they are running. Okay, so the sequential cell count should not change at any point, and I'll tell you an open question. This will be a question that will come to your assessment at any point. This question will be there. So I'm giving an open question to you now. Yeah, somebody has any doubt?
So we will have to revisit the code, right, and correct if it
You should
increases.
not revisit the code. The
Okay.
code should not be revisited. If the flip-flop count is increasing, what you have done that mistake, that you will have to see during implementation. At floor planning, did you do anything blunder? At placement, did you do any blunder? At routing, did you do any blunder? Whatever. Yeah. At what stage you did any issue, you have to see that. If flip-flop count is increasing, means you have done the biggest blunder. You have to be put in jail. That is the level of blunder we see it.
Okay.
Because you have changed the functionality of the design chip, right? The functionality of the chip, owner is the designer only. The functionality of the chip, the owner is the designer who writes the RTL.
Yeah, but this is, I mean, if it is, this detection is happening after synthesis, right, sir? We haven't yet gone to the physical design, correct?
Yeah, we haven't gone, but I'm saying when we are going, we will always have to ensure that the sequential cell count is not increasing or decreasing.
Right. We have to keep this in mind at every stage, is what you are saying.
Yeah, at every stage, we will have to dump a report and see that it is the same.
The validation, actually.
Yeah, because you are doing some work, no? In floor planning, you will do some task. In placement, you will do some task, correct?
Okay. I thought only here the number is increasing after the synthesis is what I was.
No. I am saying synthesis number is a reference.
Reference. Okay. Sorry. Okay. Thank you.
Yeah.
So this behaves as a primary checklist for each stage, right?
Yes. Certain checklist from here we will have to take it on. So from here, the most important factor is the sequential cell count. Second will be the timing. If you have met the timing at synthesis, what is the timing that you have met and what is the slack that you are getting? If that is the second reference we will have to take from synthesis. See, in actual industry, synthesis is not part of physical design. Synthesis is part of the design. The designer takes the ownership of doing synthesis. He writes the design, he do the synthesis. For him, this gives him a better understanding about his design. Like you have written an up-down counter and you are doing synthesis. Did that give you a understanding about your design? Did that show you, wow, oh, my design takes 4 flip-flops, my design takes this many combinational cells. It is giving you an understanding, right? That level of that things will be understood by designer. So that's why synthesis is part of designer's job. Okay. Now let's have an area estimation for this particular design. Okay. We are not taking it up-down counter because up-down counter is very small. Okay. But for area estimation, we will take this numbers. How do you estimate the area? Okay. First of all, yeah, I told you about the design area. Total design area is coming to be something this, which is 4808993.0064 the micrometer square. Okay. Now let me I'll come to my notepad. I will show you how does this area estimation is done. But just look into this, okay? Just look into this because this is on my machine. So we will not be able to switch back. If you want, you can note it down, okay? See, here you see here the combinational area is specified. non-combinational area is specified. What is non-combinational area?
The sequential area.
Yeah,
Sequential area.
Yeah, sequential area. What is sequential area is, see, you have 28,948 cells. In that, every cell, the area is there. No, you have seen in the dot lib, for every cell, there is an area that is shown, right? You remember?
Yes.
Yeah. In that every cell, there will be an area. For all these 28,948, this is the accumulated area here, total area of this 28,948. And the combinational cell count is this much, and the corresponding combinational area is this much. And remaining buffer, inverter, everything. Okay. And see here, it is telling that macro area. What is macro?
RAM.
Memory.
Yeah.
Cache.
Yes. So we were
Cache.
telling, no, while studying the technology library, there are standard cells, there are IOPAD cells, there is macro cells.
Macro cells.
Yeah. In that macro, so in this design, it doesn't have any macro. It has only standard cells and combinational cells. So that is why it's showing that macro area is 0. If there is any macro area, then we will have to accommodate that also. And here it is saying net area. See, net area is something that is not actually there, but it is giving you an estimate of your net area might be something this much. But actual nets is not there in synthesis, because in synthesis you have the timing aspects, you have the area aspect from all picked up from the standard cell library only. It doesn't have any information about the metal layers that is there, which is going to come in the next steps, floor planning and all, which is not there in those information are not there in the .lib. So all these information, correct? All these information are picked up from where? From .lib only, correct?
Yeah.
Yeah. So you don't have any other information that is coming from Sky and coming in this report. It is all the report, the values that is picked up from the standard cell library only. Now, if you want, you can note this number. I'm going to my iPad now and I use my pen. So I'm stopping here. So I was telling about slow, fast, and typical. So I missed out this typical corner. Typical corner is another corner that's available, and it will be like in between slow and fast. There will be values, timing values in that library. Okay, now we are going for this estimation, area chip size estimation. Okay, so the design area that you saw in that report is, what was the value?
4808993.
4808993. Fine.
0.0065.
Fine, that's okay. So this is micrometer square. Okay. Now this means what? What is the size of my chip is I'll pick someone and I will ask them to do that. Okay. Sangaran, can you unmute your mic?
Yes, sir.
Yeah. Sangaran, you're from?
I'm from Coimbatore.
No, I'm like, which year?
Oh, no, I was an working professional.
Oh, you're
I'm an
working.
embedded
So,
trainer.
okay, fine. So, Sankaran, can you give me the square root for this number? Square root value for this number? Just open your calculator and do the square root for this.
Oh. So it is 2192.
2192.
219.
Correct?
Yeah, 0.94.
That's fine. 2192.9. Okay, 0.9. Okay. So this is the square root for this value, which means your chip size is going to be 2192.9 cross 2192.9. So we can take it as 2193 cross 2193. That is, your chip is going to be 2193 micrometer cross 2193 micrometer. You're getting, everyone?
Yes, sir.
Yes, sir.
But actually, this is not the correct number. Okay, the correct number, how it should be estimated, I'm coming down. Okay, so this design area is there. No, what does this comprises of? Standard cells and macros, correct?
Yes, sir.
No, usually I'm saying now right here you have macro 0, but you have standard cells and macros, correct? Now what value you are having here is for standard cells alone. For macros, it's not there. Now, to estimate the size of the chip, what is the thumb rule that we usually follow in industry is total standard cell area that you have here, this has to be multiplied by 1.2. Okay. Can someone multiply this value in I'll pick someone. Wait. Vineet. Palle Vineet. Vineet, can you unmute? Okay, anyone else, please say. Just multiply this number into 1.2.
577
577
0791
0791
0.6.
0.6 micrometer square, correct? So why I am doing into 1.2 is because, see, I have to place all my components of standard cells inside the chip, and I'm going to, these are my flip-flops and other gates. These I will have to connect some wires between them, correct? There will be nets coming into picture. Actual nets will come into picture. So while connecting to the nets, I cannot go on connecting like one beyond one. I mean, it will be like it is a random thing. Random connection will be there. For that connecting area, net connecting area only, I'm estimating that area to be 1.2 times of each cell area. That's why I'm accounting this 1.2 number. So once you do this 1.2 times, mostly you'll be able to achieve the area required for the implementation of your design. Suppose you are using macros. Suppose you have macros and there is corresponding macro area associated with that. Then what you have to do is you have to multiply 1.5 times the area that is there. Right now it's 0, but I'm saying if it's there, then you have to do a 1.5 times and you will have, say, X value. So total area will be, total chip area will be your total macro area X plus your standard cell and combinational area, which is going to be this one. So now your chip area will be the square root of total chip area will be the size of your chip. So now since we don't have macros, now anyone take the square root of this 5770791.7.6?
2402, sir.
2402
02
cross 2402 is my chip size. Now you see, previously you had only 2193 cross 2193. Now it is 2402 cross 2402. That's because you had given this 1.2x time, which is required for connecting the nets. Any doubt until this?
Sir, what about IO pads?
IO pads are anyway going to come on the periphery, right? It is not going to be inside this.
It doesn't come as part of the chip area. It's just the extension from there.
Yes, this is only the core area.
Oh. So one more thing. Since I asked it before, if we are giving this some UPF file as an input to the synthesis tool, so will that also be accounted into this area estimation?
Yeah. So UPF, if you are doing it, taking it and giving it to the synthesis, it will have its own reports, right?
Yeah.
So we will be accounting to that.
Okay. So because when you're doing power planning, we add the power switches in the placement stage, right?
Yes.
So so the area won't be visible in the post synthesis stage.
Yes, it will not be. But what you are putting out here, you are just ensuring the connection between the cells, okay? That if it is sufficient space is there for the connection between the cells. If there is sufficient space for the connection of the macros, that is, you are adding 1.5 times for that. That is the two things that will ensure. For considering the isolation cells, for considering the power switches, for any other aspects that you are doing, will be accounted at floor plan placement stages, because that is going to be very minimal only. That will not be going to be like some thousands of cells. It will be very less cells only.
Okay.
Any doubts? Okay. So, okay. Next is, so this is the estimation, resource estimation. Now we will take forward this and go for floor planning placement. In tomorrow's session, if I start few aspects, then it will take some time. So in tomorrow's session, we will see about certain aspects of STA, the static timing analysis. We'll see how the timing actually is getting estimated. What are the other aspects of timing that is there that has to be considered? Those things we will see tomorrow. Meanwhile, any other doubts if you have, and I think you have exam today. So any other doubts in the previous classes, anything is there, please go ahead and ask.
Not a doubt. I just wanted to check on something, right? So so if we want to try out the netlist part, we need the PDK, right? So, and that you only get once you sign up with some foundry, right? Like SCL. So I was looking at if there are open source PDKs, and I figured out there are few. So can we use those and do the same process? Because in their documentation they were talking about using some other open source tool like LibreLane or something similar, right? So is it something we could try out? I assume the process would be same, right? And it should work.
Yeah. If you are going to use open source tools, yeah, you can take it up there. It's already available in internet.
Yeah.
Yeah, you can take up, and there are open source PDKs also. You can take it. A synthesis part and all is very straightforward at using open source tools. You can take it up. Yosis is a tool that is open source. You can take that and do synthesis.
Okay. Okay. Yeah. I just want.
Fine. Anirudh, you said something. How can we learn to write SDC file? Writing in SDC, I think I showed you, Anirudh. One aspect I showed you. By end of the course, you will be able to get other aspects of SDC. We'll slowly add on other aspects of SDC, like setting up input delay, setting out output delay. There is other more thing is called as uh, if you have any false path in your design, and there is clock uncertainty. If you want to specify, there are all those aspects are there, which on the go when class goes on, you will come to know.
Okay, sir. Thank you.
Anyone else? Ramya. Ramya. Okay, you didn't say anything. Sorry. Fine. Just to give me a moment, I'll just see whether I have missed anything for today's class. 1 minute. Yes. One more thing that I have about to tell you. Okay, so here you write the RTL, correct? This is a question for everyone. You write the RTL, and how do you check the functionality of this RTL?
By simulation.
Verification.
Yeah, by simulation, you write a test bench and verify, correct?
Yes.
Okay.
Sir, test
Yeah,
bed.
yeah, but that is not the question. The question is, once you take the RTL technology library constraints you feed and do the synthesis, and you got a netlist. Now, how do you verify this netlist whether whatever you are written in the RTL is being implemented correctly? How do you check this netlist.v? Anirudh?
Sir, in the reports we can check what are the sequential components and how many.
That and all it will tell. Like I have some X flip flop, Y cells, all those things are there. But I wanted to know if you are right, if you have written one up down counter and it is counting 1, 2, 3, 4 until 15, and from 15 it's counting for down counter until 1 for this RTL. I wanted to check whether this is happening in my netlist or not. How do I do that?
I don't know, sir.
Don't say don't know. Just think it's a very simple thing only.
Sir, test bench, sir.
Exactly. Tejas. You're from?
Sir,
Tejas, you're from?
this is Tamil Nadu, sir.
I didn't get.
Sir, Anipesh sir, Tamil.
Oh, okay, yeah, fine. Tejas, okay, got now. Okay, so basically the test bench that you have used for writing, for checking this RTL, right? The same test bench you can use for checking the netlist, because netlist is again a Verilog only, right? The netlist that it will also have module, end module, and other gate level components only here. It will have a flip-flop, D flip-flop will be there, and inverter, other components and all is there, that's all. So you write a test bench, you use the same test bench, preferably you use the same test bench and instantiate this netlist.v inside the test bench and pass value and check whether it is working or not. But if you see, it will have the components. The netlist, this netlist has components of D flip flop, and it has components of inverter, it has components of AND gate. All these things are no. So for these things are the components that is picked up from standard cells, correct?
Yes, sir.
So this will have these cells will have its own Verilog models available. It will have its own Verilog models. D flip flop dot v, inverter dot v, and dot v available along with the PDK, which I will show you tomorrow. Okay, I'll show you tomorrow in the starting of the class itself about this. In the PDK, like you have dot lib and dot db, you will have dot v also. Dot v for all the cells that is there inside the standard, inside the dot lib. Now what you will have to do for doing the functional simulation using test bench is, you will have the test bench first. Second thing, you will have the netlist. And third thing is, you will have the Verilog models for this gates that is there in the netlist. So once you have all these three things in picture, then you will be able to do the functional simulation and you will be able to see it. Are you guys getting it, or you got confused now?
So Verilog model.
Verilog model are the models for the D flip flop that is being called inside this netlist.
Okay.
So maybe tomorrow's class, yeah, we'll continue in tomorrow's class. We'll start from the same place where we are leaving it today. Tomorrow's class, I will open up all the Verilog models for all the standard cells and show you how does that Verilog models look. Those Verilog models are only used for simulation. Just remember this. Only these Verilog models are used for simulation. They are not taken for anything in implementation. Only these are used for the designer to check whether the netlist that is generated is correct or not. For that verification only it is used.
Okay.
So when the netlist is taken for simulation, it is called GLS, which is called gate level simulation. When your RTL you are simulating, it's a normal functional simulation. When your netlist, you are taking the netlist instead of RTL, you are taking the netlist. One is the netlist. Next is the test bench for this netlist, and third is the Verilog models for the components inside the netlist. All these three things you take and you do the simulation and you observe the waveform and check whether you are able to see the functionality is met or not. Then you say it as gate level simulation. Okay, we'll take one more minute. Any doubts? Yeah, go ahead, Rohit.
Okay. So is the verifying the netlist with the test bench the same as logic equivalence checking, or is that a separate thing?
It is equal to logical equivalence checking. LEC is done by the physical design team, but gate level simulation is done by the designer who is writing the RTL. For him, he will have to see it whether my design is working or not.
Okay.
Yeah. Fine, let's close this. We will continue with this same thing tomorrow and see other aspects also. Okay then. Bye.
Thank you, sir.
Thank you. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. Bye.
Thank you, sir.
Thank you. We can stop the recording,
Sir.
Physics Wala.